You are listening to MySQL for Developers, a practical guide. Like and subscribe to keep up to date on our latest audiobooks. MySQL for Developers, a practical guide. Chapter 1, Getting Started with MySQL for Developers. Welcome, aspiring database navigators and application architects. If you're holding this book, chances are you're embarking on a journey to build dynamic, data-driven applications, and you've chosen MySQL as your trusted companion. This isn't just a manual. It's your practical guide to understanding, utilizing, and optimizing one of the world's most popular relational database management systems from a developer's perspective. In today's interconnected world, almost every application, from a simple blog to a complex e-commerce platform, relies on a database to store and retrieve information. As a developer, your ability to design robust schemas, write efficient queries, and integrate seamlessly with your backend code will significantly impact your application's performance, scalability, and maintainability. This chapter sets the stage. We'll explore what MySQL is, why it holds such a prominent position in the developer community, and most importantly, how to get it up and running on your machine so you can start coding and experimenting right away. 1.1 What is MySQL and why use it? At its core, MySQL is an open-source relational database management system, RDBMS. This mouthful just means it's a software application designed to help you create, maintain, and interact with relational databases. But what exactly is a relational database? Imagine organizing information not in a single, giant, unstructured ledger, but in separate, highly organized tables, much like spreadsheets. Each table represents a distinct entity, like users or products, and each row in a table represents a record of that entity. Columns within a table define the specific pieces of information, like username, email, product price. The relational part comes from the ability to define relationships between these tables, allowing you to link data logically, for instance, connecting a user to the posts they've written. The language we use to communicate with MySQL and most other relational databases is SQL, which stands for Structured Query Language. SQL is the industry standard for managing and querying data in relational databases. It's a declarative language, meaning you describe what you want to achieve, and the database figures out how to do it. Why has MySQL become a developer favorite? Open source and cost-effective. MySQL is freely available under the GNU General Public License, making it an incredibly attractive option for startups, small businesses, and personal projects. Even the enterprise version offers compelling value. This open nature has fostered a massive, vibrant community. Performance and reliability. MySQL is known for its speed and robustness. It's engineered to handle large datasets and high transaction volumes efficiently. With the InnoDB storage engine, which we'll discuss later, it provides ACID compliance, atomic, consistent, isolated, durable for reliable transaction processing, crucial for critical business operations. Ease of use and learning curve. For its power, MySQL is relatively straightforward to set up and learn, especially for developers familiar with programming concepts. The SQL syntax is intuitive and readable. Scalability. MySQL can scale both vertically, more powerful server, and horizontally, distributing data across multiple servers using replication and sharding. This allows applications to grow significantly without needing a complete database overhaul. Vast ecosystem and community support. Being so widely used, MySQL boasts an enormous ecosystem of tools, libraries, frameworks, ORMs, and an active community. If you run into a problem, chances are someone else has faced it and discussed a solution online. Cross-platform compatibility. MySQL runs on virtually any operating system, Linux, Windows, macOS, and more, making development and deployment flexible. Integration with popular languages frameworks. Whether you're building with Python, Django, Flask, Node.js, Express, PHP, Laravel, Symfony, Ruby, Rails, Java, Spring, or Net, there are mature, well-supported connectors and ORMs that make integrating MySQL into your application seamless. From small personal websites to large-scale web applications, enterprise systems, and even data warehousing solutions, MySQL proves to be a versatile and powerful choice. Its combination of performance, reliability, and community support makes it an excellent database for developers. 1.2. Installing MySQL. Before we dive into writing SQL, you need a MySQL server running on your machine. There are several ways to achieve this, ranging from native installations to containerized environments. For developers, a containerized approach, like Docker, is often the most convenient as it provides a clean, isolated, and easily reproducible environment. Option 1. Using Docker, highly recommended. Docker revolutionized how developers set up their environments. It allows you to run applications and their dependencies in isolated containers, ensuring consistency across different machines and avoiding conflicts with existing software. If you don't have Docker installed, you'll need to do that first. Search Install Docker Desktop for your OS. Once Docker is ready, open your terminal or command prompt and run the following command. This will download the official MySQL 8.0 image. If you don't have it, create a new container named MySQL DevDB, set a root password, and open port 3306, the default MySQL port, on your host machine to allow connections. Docker run name MySQL DevDB miscroot password equals mistrong password. P33633060 MySQL 8.0. Let's break down this command, Docker run. The command to run a new container. Name MySQL DevDB assigns a convenient name to your container. You'll use this name to refer to it later. Miscroot password equals mistrong password. Sets the password for the root user inside the MySQL server. Replace mistrong password with a real strong password. P33630306. Maps port 3306 on your computer host to port 3306 inside the Docker container. This is how your applications will connect to MySQL. DMySQL 8.0 specifies the Docker image to use MySQL and its version 8.0. The D flag runs the container in detached mode in the background. After running this, Docker will download the image and start the container. You can check its status with Docker PS. You should see an entry for MySQL DevDB with status indicating it's up. Persisting data with Docker volumes. By default, data inside a Docker container is ephemeral. If you remove the container, your data is gone. For a development database, you'll want to persist your data. A better Docker run command using a named volume would be Docker volume create MySQL data. Docker run name MySQL DevDB miscroot password equals mistrong password. P33633006 v MySQL data /var/lib/ MySQL dmysql 8.0. Here, v MySQL data /var/lib/ MySQL creates or uses existing a Docker volume named MySQL data and mounts it to the MySQL data directory inside the container. This ensures your database changes persist even if you stop or restart the container. To stop the container, Docker stop MySQL DevDB. To restart it, Docker start MySQL DevDB. To remove it and its data if no volume used, Docker rm MySQL DevDB. Option 2, native installation, operating system specific. If you prefer a direct installation or can't use Docker, here's a general guide. Refer to the official MySQL website, dev.mysql.com/downloads/mysql/ for the most up-to-date and specific instructions for your operating system. Windows. Download the MySQL installer for Windows, MSI file. Run the installer and choose Developer Default Setup Type. Follow the prompts to configure the server, including setting a root password. Ensure MySQL is added to your system's path environment variable for easy command line access. macOS, using Homebrew recommended. If you have Homebrew, open your terminal and run. Brew install MySQL at 8.0. Hash to start MySQL service. Brew services start MySQL at 8.0. Hash to restart. Brew services restart MySQL at 8.0. Then, typically, you'll run MySQL secure installation to set up the root password and secure the installation. Using official DMG installer. Download the macOS DMG archive from the MySQL website and follow the installation wizard. Linux, Debian/Ubuntu. Sudo apt update. Sudo apt install MySQL server. Sudo MySQL secure installation hash follow prompts to secure your installation. Linux CentOS rhel. Sudo dnf install MySQL server hash, or yum on older versions. Sudo systemctl start MySQL. Sudo systemctl enable MySQL. Sudo MySQL secure installation. After native installation, always run MySQL secure installation. This script guides you through setting a root password, removing anonymous users, disallowing remote root login, and removing the test database. It's crucial for security. 1.3 Connecting to MySQL. Once your MySQL server is running, it's time to connect to it. We'll look at two primary ways: the command line client and a graphical user interface, GUI, tool. Using the MySQL command line client. This is the most fundamental way to interact with MySQL. It's lightweight, fast, and indispensable for developers, especially for scripting or quick checks. Open your terminal or command prompt and try to connect as the root user or MySQL on some systems. MySQL uroot p. Uroot specifies the username root. P prompts you for the password. Enter the password you set during installation, e.g., mystrong password if you use the Docker example. If successful, you'll see the MySQL prompt. Congratulations, you're connected to your MySQL server. To exit, type exit or quit and press enter. Introduction to GUI tools, MySQL Workbench/dbeaver. While the command line is powerful, GUI tools offer a visual way to manage databases, build queries, and inspect schemas. They are highly recommended for daily development. MySQL Workbench, official, download, dev.mysql.com/downloads/workbench/. Features: comprehensive tool for database design, diagrams, SQL development, query editor, execution plans, database administration, user management, server status, and data migration. Connecting. Open MySQL Workbench. Click the plus icon next to MySQL Connections to add a new connection. Connection name, give it a meaningful name, e.g., local MySQL 8.0, hostname, 127.0.0.1 or localhost. If using Docker, ensure your container's port is mapped correctly. Port 3306. Username, root, password. Click Store in Keychain Vault and enter your root password. Click Test Connection to verify. Click OK to save and then click on your new connection to open a query tab. dbeaver Universal Database Client. Download dbeaver.io/download/. Free and open source, supports a wide range of databases, not just MySQL. Excellent choice if you work with various database systems. Features: SQL Editor, Data Viewer Editor, Visual Query Plans, Schema Browser, Data Export Import. Connecting, open dbeaver. Click Database, New Database Connection. Select MySQL from the list and click Next. Host, localhost or 127.0.0.1, port 3306. Username, root. Password, enter your root password. Click Test Connection to verify. Click Finish. For the purpose of this book, most SQL examples will be presented as plain SQL statements that you can run in either the command line client or your chosen GUI tool. It's a great habit to run them yourself to see the results. 1.4 A quick tour of MySQL concepts. Now that you're connected, let's get a feel for the basic structure within MySQL. Databases or schemas. A MySQL server can host multiple databases, each typically representing a distinct application or system. You can think of a database as a container for related data. In MySQL, the terms database and schema are often used interchangeably. To see the databases currently on your server, Show Databases, you'll likely see some default databases like Information Schema, MySQL, Performance Schema, and SIS. These are system databases that MySQL uses internally. Avoid modifying them directly. Creating your first database. Let's create the blog platform database that we'll use for all our examples throughout this book. Create database blog platform. Now, if you run Show Databases, again, you'll see blog platform in the list. Selecting a database for use. Before you can interact with tables within a database, you need to tell MySQL which database you want to work with. This is done with the use statement. Use blog platform, you'll get a message like database changed. From this point onwards, any table-level commands you issue will apply to the blog platform database, unless you explicitly specify another database. Tables, columns, and rows. Inside a database, data is organized into tables. Each table has columns, which define the type of data and named fields, and rows, which are individual records or entries. For example, our blog platform database will eventually have tables like users to store user information, posts for blog articles, and comments for user comments on posts. Since we just created the database, it's currently empty. To see an empty list of tables, show tables. We'll learn how to create these tables, define their columns, and populate them with data in the next chapter. SQL versus MySQL-specific commands. It's important to understand the distinction. SQL, structured query language. This is the standardized language for managing relational databases. Commands like select, insert, update, delete, create table, alter table are standard SQL and would work similarly across many different RDBMS like PostgreSQL, SQL Server, etc. MySQL-specific commands features. While MySQL adheres largely to SQL standards, it also has its own extensions, functions, and administrative commands. For instance, show databases and use database name are MySQL-specific convenience commands, though standard SQL has information schema views to achieve similar results. We'll always clarify if a command or feature is particular to MySQL or broadly applicable SQL. Summary of Chapter 1. In this foundational chapter, we've laid the groundwork for your journey into MySQL. You now understand that MySQL is a powerful, open-source RDBMS that uses SQL for data interaction and query. You've learned about its key advantages for developers, its position in the tech ecosystem, and, most importantly, you've successfully set up your development environment by installing and connecting to a MySQL 8.0 server. You can now connect to MySQL via the command line or a GUI tool. Create and select databases. List existing databases and tables. With your MySQL server humming along, you're ready to dive into the core concepts of database design and start manipulating data in the next chapter. Get ready to transform your development skills. Chapter 2, The Foundations, Database Design and Schema. Congratulations, you have your MySQL server up and running. But a database server is just a sophisticated storage cabinet. You need to organize its contents effectively to make it useful. This is where database design comes in. For a developer, understanding good database design principles isn't just a nicety. It's fundamental to building applications that are performant, scalable, maintainable, and robust. In this chapter, we'll dive into the world of relational database principles, unravel the concept of normalization, explore the crucial decisions involved in choosing the right data types, and finally, learn how to translate your design into a working MySQL schema using Data Definition Language, or DDL. We'll build our sample blog platform database, which will serve as our playground throughout this book. 2.1 Understanding Relational Database Principles. At the heart of every relational database are a few core concepts that govern how data is structured and linked. Entities, attributes, and relationships. Imagine you're designing a system for a blog. What pieces of information do you need to store? Entities. These are the distinct, real-world objects or concepts that your database needs to keep track of. In a blog, entities might include users, posts, and comments. Each entity typically corresponds to a table in your database. Attributes. These are the characteristics or properties that describe an entity. For a user entity, attributes might be username, email, password hash, and created at. Each attribute typically corresponds to a column in a table. Relationships. This is how different entities are connected to each other. For example, a user writes many posts. One-to-many relationship. A post has many comments. One-to-many relationship. A post can belong to many categories, and a category can have many posts. Many-to-many relationship. Understanding these connections is crucial for designing tables that reflect your data's true nature. Primary keys, foreign keys, and unique keys. These special types of keys are vital for defining relationships and ensuring data integrity. Think of them as the glue that holds your relational database together. Primary key, PK. This is a column or a set of columns that uniquely identifies each row or record in a table. Uniqueness. No two rows can have the same primary key value. Non-nullability. A primary key column cannot contain null values. Stability, primary key values should ideally never change. Example, in a user's table, a column like id, an auto-incrementing number, is a perfect primary key. It guarantees that every user has a distinct identifier. Most relational databases, including MySQL with the InnoDB storage engine, use the primary key to physically organize the table's data, making lookups by primary key extremely fast. Foreign key, FK. A foreign key is a column, or set of columns, in one table, the child table, that refers to the primary key of another table, the parent table. It establishes a link or relationship between the two tables. Referential integrity. Foreign keys enforce referential integrity, meaning that you cannot have a foreign key value that does not exist as a primary key in the parent table. For example, if you have a comments table with a userid foreign key, you cannot add a comment written by a userid that doesn't exist in the user's table. Example, in our posts table, a userid column would be a foreign key referencing the id column in the user's table. This links a post to its author. When you define a foreign key, you can also specify an action to take when the parent record is deleted or updated. Common actions include on delete cascade. If the parent record is deleted, delete all child records. E.g., delete a user, delete all their posts. On delete set null. If the parent record is deleted, set the foreign key in the child record to null. E.g., if a user is deleted, their comments might remain but their userid becomes null. On delete restrict, default for some systems. Prevent the deletion of the parent record if there are child records referencing it. On delete no action, similar to restrict, but differs in deferred checking, not relevant for MySQL's immediate checking. Unique key. Similar to a primary key, a unique key also enforces uniqueness for a column or set of columns. However, unlike a primary key, a table can have multiple unique keys. A unique key column can typically contain null values, though usually only one null for consistency. Example, in our users table, both username and email should probably be unique, as two users shouldn't share the same username or email address. You could define unique keys on these columns. These keys are the building blocks for well-structured and reliable database schemas. 2.2 Introduction to Normalization. Normalization is a systematic approach to designing relational database schemas that minimizes data redundancy and improves data integrity. It aims to eliminate anomalies when inserting, updating, or deleting data. While there are several normal forms, 1NF, 2NF, 3NF, BCNF, 4NF, 5NF, practical application often focuses on reaching 3NF, as it strikes a good balance between data integrity and performance. Let's illustrate with simple examples. First, normal form, 1NF, eliminating repeating groups. A table is in 1NF if each column contains only atomic indivisible values. No multi-valued attributes in a single cell. Each row is unique, identified by a primary key. Bad example, not 1NF. Imagine a posts table where you store categories as a comma-separated list in a single column. Posted title categories. 1 Intro to SQL Technology, Programming. 2 Joys of Python, Programming. This is not 1NF, because the categories column contains multiple values. What if you want to find all posts in technology? You have to parse strings, which is inefficient and error-prone. Good example, 1NF. To achieve 1NF, we'd split categories into a separate table and use a junction table for the many-to-many relationship. Posts table, posted title. 1 Intro to SQL. 2 Joys of Python. Categories table, categoryed name. 1 Technology. 2 Programming. Post categories, junction table for many-to-many. Posted categoryed. 1 1. 1 2. 2 2. Now each column is atomic, and each row in post categories represents a single link. Second normal form, 2NF. Eliminating partial dependencies. A table is in 2NF if it is in 1NF. All non-key attributes are fully functionally dependent on the entire primary key. This applies mainly to tables with composite primary keys, keys made of multiple columns. Bad example, not 2NF. Consider a table combining post details and author details. Posted PK, authorid pk, post title author name author mail. 101 SQL Basics, John Doe John at example.com. 101 SQL Joins, John Doe John at example.com. Here the primary key is posted authorid. Post title depends on posted, a part of the primary key, but author name and author mail depend only on authorid, another part of the primary key, not the entire composite key. This leads to redundancy, John Doe's details repeated for every post. Good example, 2NF, separate author details into their own users table, posts table. Posted authorid, FK post title. 101 SQL Basics. 101 SQL Joins. Users table, authorid PK, author name author mail. 101 John Doe John at example.com. Now, author name and author mail fully depend on authorid, which is the primary key of the user's table. Third normal form, 3NF, eliminating transitive dependencies. A table is in 3NF if it is in 2NF. All non-key attributes are functionally dependent only on the primary key and not on any other non-key attribute. Bad example, not 3NF. Imagine a memberships table for a club. Memberid PK, member name clubid, club name club address. 1 Alice 1 Tech Club, 123 main cent. 2 Bob 1 Tech Club, 123 main cent. 3 Carol 2 Reading Guild, 456 Elm cent. Here, club name and club address are non-key attributes, but they depend on clubid, which is also a non-key attribute. This is a transitive dependency. If clubid changes, or if we need to add a new club without any members yet, we would have issues. Good example, 3NF, separate club details into their own table, memberships table. Memberid PK, member name clubid FK. 1 Alice 1, 2 Bob 1, 3 Carol 2. Clubs table, clubid PK, club name club address. 1 Tech Club, 123 main cent. 2 Reading Guild, 456 Elm cent. Now, club name and club address directly depend on clubid, which is the primary key of the club's table. Higher normal forms, BCNF, 4NF, 5NF. Briefly, Boycott normal form, BCNF, is a stricter version of 3NF, mainly addressing cases with overlapping candidate keys. Fourth normal form, 4NF, deals with multi-valued dependencies, and fifth normal form, 5NF, deals with joined dependencies. For most developer-level applications, achieving 3NF is sufficient and highly beneficial. Deeper normalization might become necessary for complex data warehousing or highly academic database design. But it's often overkill for everyday transactional applications. When to denormalize and the trade-offs. While normalization is great for data integrity and reducing redundancy, it can sometimes lead to very complex queries involving many table joins, which can impact read performance. Denormalization is the intentional introduction of redundancy to improve query performance, often by combining data from multiple tables into a single table. Common scenarios for denormalization: reporting and analytics. Data warehouses often denormalize heavily for fast analytical queries, caching frequently accessed data, storing a derived or frequently joined value directly in a table. For instance, storing a post comment count directly in the posts table, even though it can be calculated from the comments table. Performance bottlenecks. If a highly normalized schema consistently leads to slow queries despite indexing, denormalization might be a necessary evil. Trade-offs of denormalization: increased data redundancy. The same data is stored in multiple places. Increased storage space, more data needs to be stored. Data inconsistency risk, data needs to be updated in multiple places. This requires careful management, e.g., using triggers or application logic to keep redundant data synchronized. Loss of flexibility, changing the schema might be harder. As a general rule, start with a normalized design, aim for 3NF. Only denormalize when you identify a genuine performance bottleneck that cannot be solved with indexing or query optimization, and be prepared to manage the increased complexity of data maintenance. 2.3. Choosing the right data types. The data type you choose for each column in your table is crucial. It determines how MySQL stores and manipulates the data, impacting storage space, query performance, and the integrity of your information. Always choose the smallest data type that can reliably hold the expected range of values. Here's a breakdown of common MySQL data types relevant to developers. Numeric types. Used for numbers: TINYINT, SMALLINT, MEDIOMINT, INT, BIGINT. For whole numbers, integers. They differ in the range of values they can store, with TINYINT being the smallest, 1 byte, -128 to 127 signed, 0 to 255 unsigned, and BIGINT the largest, 8 bytes, very large numbers. Developer tip: INT is often a good default for general-purpose integer IDs or counts. Use BIGINT only when numbers might exceed the INT range, approx. 2 billion. Add unsigned if values will never be negative, effectively doubling the positive range. Decimal, MD, for fixed point numbers, ideal for financial data where precision is paramount. M is the total number of digits. D is the number of digits after the decimal point. Decimal, 5, 2 can store values like 999.99. Developer tip: always use decimal for monetary values. Never use float or double for money due to floating point precision issues. Float, P, and double, for floating point approximate numbers. Float is single precision, 4 bytes, double is double precision, 8 bytes. Developer tip: use these when exact precision is not critical, such as scientific measurements or general calculations where slight deviations are acceptable. String types, textual data. Used for text: char L, fixed length string. If you declare char 10 and insert hello, it will pad the remaining 5 characters with spaces, up to 255 characters. Developer tip: only use char when you know the length will always be fixed, e.g., country codes like US, GB if they are always 2 characters. Varchar L, variable length string. It stores only the characters you provide, plus 1 or 2 bytes for length information. L is the maximum length, up to 65,535 bytes, depending on row size limits. Developer tip: the most common choice for general-purpose strings like names, titles, emails. Always choose a varchar over char unless you have a specific, justifiable reason. TINYTXT, text, MEDIOMTXT, LONGTXT. For larger blocks of text. They differ in maximum storage size. TINYTXT is 255 bytes, LONGTXT can hold up to 4 GB. Developer tip: use text for blog post content, comments, or larger descriptions. They are stored off-row if large, meaning fetching them might incur an extra disk read, but they are flexible. Enum, val1, val2. A string object with a value chosen from a list of permitted values that are specified at table creation time. Developer tip: useful for fixed sets of small choices, e.g., status enum, draft, published, archived. They are stored efficiently, as numbers internally, but can be less flexible if the list of values changes frequently. Set val1, val2. A string object that can have 0 or more values, each of which must be chosen from a list of permitted values specified when creating the table. Developer tip: less common than enum. Useful for flags or configurations where an item can have multiple predefined attributes, e.g., options set email notifications, SMS notifications. Date and time types. Used for temporal data. Date stores dates only YYYYMMDD. Time stores times only HHMMSS. Data time FSB. Stores date and time YYYYMMDD HHMMSS can have an optional fractional seconds precision, 0 to 6. Range 1000 to 1 to 1000 to 9999 to 12 to 31 23 59 59. Developer tip: good for general purpose recording of exact moments in time. Timestamp FSB stores date and time YYYYMMDDHH represents points in time relative to the Unix epoch 1970 to 1 to 1 UTC. Range 1970 to 1 to 1001 UTC to 2038 to 1 to 19314.7 UTC. Developer tip: timestamp columns are automatically updated. For example, default CURRENTTMESTMP on update CURRENTTMESTMP is common for update det columns. They are also time zone dependent, stored in UTC, converted to session time zone on retrieval. If cross-time zone consistency is critical, ensure your application handles time zones correctly or simply use DATTIME and store UTC explicitly. Year stores a year in 2 or 4-digit format. Binary types for storing raw binary data. TINYBLOB, blob, MEDAUMBLOB, LONGBLOB, binary large objects. Similar to text types but store binary data, like images, audio, small files, without character set considerations. Developer tip. Generally, it's better to store binary files on a dedicated file storage service, like AWS S3, and store only the file path or URL in the database. Storing large blobs directly in the database can impact performance and backup sizes. JSON type, MySQL 5.7+. Stores JSON documents, JSON. Stores JSON documents directly, allowing MySQL to parse, validate, and optimize storage for them. You can directly query fields within a JSON document. Developer tip. Useful for flexible, schemaless data, e.g., user preferences, product attributes, that doesn't fit neatly into traditional relational columns. Offers a middle ground between relational and NoSQL databases. Do not abuse JSON types to avoid proper normalization. Use them only when the data truly is unstructured or highly variable. Best practices for data type selection. Use the smallest possible type. Smaller data types use less disk space and memory, leading to faster queries. Match type to data. Use INT for integers, decimal for money, specific date types for dates, etc. Be explicit with constraints. Use not null when a value is mandatory, unsigned for non-negative numbers, ZEROFILL, though less common now for padding numbers. Consider future growth. While tiny types save space, anticipate potential increases in value ranges. It's much harder to change a INT column to BIGINT on a production system with millions of rows. VARCHAR versus text. For short to medium strings, use VARCHAR. For potentially very long strings, use text. Time zones and timestamp versus DATTIME. Understand the implications of each. If your application deals with global users and time zones, be cautious and perhaps store all DATTIME values as UTC to avoid confusion. 2.4 Designing your first schema, DDL. With an understanding of relational principles and data types, let's put it into practice by designing and creating the BlogPlatform database schema. Data Definition Language, DDL, is the subset of SQL used to define, modify, or delete database structures. We'll focus on create table and alter table. First, ensure you are using the BlogPlatform database you created in Chapter 1. Use BlogPlatform, creating tables, create table. We'll create our core tables: users, posts, comments, categories, and post categories. One users table. This table will store information about the blog's users. Create table users. IDINT, AUTONCRMENT primary key. Username varchar, 50, not null unique. Email varchar, 100, not null unique. Password hash varchar, 255, not null. Created at timestamp default, CURINTTMSTMP. Let break down this statement. Create table users. This is the command to create a new table named users. IDINT AUTOINCRMENT primary key defines the id column. INT is the data type. AUTOINCRMENT means MySQL will automatically assign a unique, incrementing integer to each new row, perfect for primary keys. Primary key designates this column as the unique identifier for each user. Username varchar, 50, not null unique. The username column, a variable length string up to 50 characters. Not null means this field cannot be empty. Unique ensures no two users can have the same username. Email varchar, 100, not null unique. Similar to username, but for email addresses. Password hash varchar, 255, not null, stores a hashed version of the user's password. It's crucial to store hashes, not plain text passwords. Varchar, 255, is a common length for various hashing algorithms. Created at timestamp default CURINTTMSTAMP, a timestamp column that automatically gets the current date and time when a row is inserted. This is great for tracking when a user account was created. 2 posts table. This table will store the blog posts themselves. Create table posts. Id int, auto primary key. User id int not null. Title varchar 255, not null. Content text. Publish at timestamp default currentTMSTMP. Update at timestamp default currentTMSTMP on update currentTMSTMP. Status enum draft published archived default draft. Foreign key userid references users id on delete cascade. New concepts here. Userid int not null. This is our foreign key linking each post to the user's table. Not null means every post must have an associated user. Text, used for content as it can store longer articles. Update at timestamp, default currentTMSTMP on update currentTMSTMP. This is a powerful feature of timestamp columns. It defaults to the current time on insertion and automatically updates to the current time whenever the row is modified. Status enum draft, published, archived, default draft, defines a limited set of possible values for the post's status, defaulting to draft. Foreign key userid references users ID on delete cascade. This defines the foreign key constraint. It states that the userid in this table must match an id in the user's table. On delete cascade means if a user is deleted, all their associated posts will also be deleted. 3. Comments table for comments on posts. Create table comments. Id int, auto primary key. Posted int not null. User id int. Content text not null. Created at timestamp default currentTMSTMP. Foreign key posted references posts, ID on delete cascade. Foreign key userid references users, ID on delete set null. Notice the crucial difference. Userid int. This userid column is not null. This allows us to have comments from non-registered users' guests. Foreign key userid references users, ID on delete set null. If a user associated with a comment is deleted, the userid for that comment will be set to null, but the comment itself will remain. This distinguishes it from the post's table's cascade behavior. 4 categories table. To hold different categories for blog posts, create table categories. Id int, auto primary key. Name varchar 50, not null unique. Simple and straightforward. An ID and a unique name for each category. 5. Post categories table, junction table. This table resolves the many-to-many relationship between posts and categories. A post can have multiple categories, and a category can apply to multiple posts. Create table post categories. Posted int not null. Categoryed int not null. Primary key, posted categoryed. Foreign key, posted references posts, ID on delete cascade. Foreign key, categoryed references categories, ID on delete cascade. Key points, primary key, posted categoryed. A composite primary key, ensuring that a specific posted and categoryed pair appears only once. 2 foreign keys, one referencing posts and one referencing categories. Both use on delete cascade, meaning if a post or category is deleted, the corresponding entry in this junction table is also removed. After running all these create table statements, you can use show tables to see your new schema in the Blogplit form database. You can also use describe table name, e.g., describe posts, to see details about a table's columns and their properties. Adding and dropping columns, alter table. DDL isn't just for creating, it's also for modifying. The alter table statement is used to add, modify, or drop columns, change data types, or add drop constraints. Adding a column, let's say we want to add a profile picture rule to our users table. Alter table users. ADD column, profile picture rule varchar 255, default profile PNG. This adds a varchar 255 column named profile picture rule and gives it a default value, ensuring existing rows get this default. Dropping a column, if that column becomes unnecessary. Alter table users. Drop column profile picture rule, modifying a column. Imagine you realize username needs to be longer. Alter table users. Modify column username varchar 100. Be careful with modify column. If you shrink a column size, you might truncate existing data. Renaming tables and columns. You can rename tables entirely. Rename table altable name to mutable name, or just rename a column. Alter table users. Change column created at, register read at, timestamp, default, currentTMSTMP. Note change column requires you to respecify the entire column definition, even if you just wanted to rename it. Understanding storage engines in NoDB. When you create a table in MySQL, you can specify a storage engine. This engine is responsible for how data is actually stored, retrieved, and managed on disk. While MySQL supports several storage engines, like MyISAM memory, InnoDB is by far the most important and recommended engine for modern applications. For a developer, understanding its default use is key. Our create table statements did not explicitly specify an engine. By default, with modern MySQL 8.0+, the default storage engine is InnoDB. This is excellent, as InnoDB provides transactions, essential for data integrity, ACID properties, allowing you to group multiple database operations into a single logical unit. Referential integrity, supports foreign key constraints. Row-level locking, allows multiple transactions to access different rows in the same table concurrently, greatly improving concurrency compared to table-level locking engines like MyISAM. Crash recovery offers robust recovery mechanisms to ensure data integrity even after unexpected server shutdowns. You can explicitly specify the engine like this, though it's usually unnecessary with the default. Create table exampletable. id primary key. Name varchar 50. Engine equals InnoDB. For almost all use cases in application development, InnoDB is the engine you want. 2.5 case study, designing a simple blog database. Let's recap the design process for our blog platform database, bringing together all the concepts we've discussed. 1. Requirements gathering. Our simple blog needs to allow users to register and log in. Let users create, read, update, and delete their own blog posts. Support comments on posts, potentially from guests. Organize posts into categories, with a post being able to belong to multiple categories. Track when users registered and when posts' comments were created or updated. 2. Entity relationship diagram, conceptual. While we won't draw a literal ERD here, a mental or sketched one would look like this. Entities, users, posts, comments, categories. Attributes, users. id, username, email, password hash created at. Posts, id, userid, title, content, published at, update at, status. Comments, id, posted, userid, content, created at. Categories, id, name. Relationships. Users 1, writes posts, many. Posts.userid references usersid. Posts 1 has comments, many. Comments posted references postsid. Users 1 makes comments, many. Comments.userid optionally references usersid. Posts many are in categories many, and categories many contain posts many. This is a many-to-many relationship resolved by a separate junction table, post categories. This conceptual model naturally leads to a normalized design. 3. Mapping to tables and relationships, DDL recap. Here's a concise summary of the DDL statements that convert our conceptual design into a physical database schema. As per the previous section, select the database to ensure we're working in the correct one. Use blog platform, create the users table. Create table users. id auto primary key. Username varchar 50, not null unique. Email varchar 100, not null unique. Password hash varchar 255, not null. Created at timestamp default currentTMSTMP. To create the posts table. Create table posts. id auto primary key. Userid int not null. Title varchar 255, not null. Content text. Publish at timestamp default currentTMSTMP. Update at timestamp default currentTMSTMP on update currentTMSTMP. Status enum draft. Published. Archived. Default draft. Foreign key userid references users ID on delete cascade. To create the comments table. Create table comments. id auto primary key. Posted int not null. Userid int null if a guest comment. Content text not null. Created at timestamp default concurrency. Foreign key posted references posts, ID on delete cascade. Foreign key userid references users, ID on delete set null. To create the categories table. Create table categories. Id int, auto primary key. Name varchar 50, not null unique. To create the post categories junction table for the many-to-many relationship. Create table post categories. Posted int not null. Categoryed int not null. Primary key posted categoryed. Foreign key posted references posts, ID on delete cascade. Foreign key categoryed references categories, ID on delete cascade. This sequence sets up our entire bloglet form database. Each table serves a clear purpose. Relationships are defined with foreign keys, and data types are chosen to optimize storage and integrity. Summary of Chapter 2. In this chapter, you've gained a deeper understanding of the foundational concepts behind relational databases and how to apply them in MySQL. You've learned about entities, attributes, and relationships, the building blocks of any database model, primary, foreign, and unique keys, how they enforce data integrity and define connections between tables, normalization, the process of organizing data to reduce redundancy and improve integrity, typically aiming for 3NF. Data types, how to choose the most appropriate type for each column to optimize storage, performance, and integrity. Data definition language, DDL, using create table to define your schema and alter table to modify it. InnoDB, the recommended storage engine for transactional applications, offering ACID properties and referential integrity. Case study, applied these principles to design and implement the bloglet form database. You now have a solid, well-structured skeleton for your database. The next step is to populate it with data and start interacting with that data using SQL's powerful manipulation commands. Get ready to insert, select, update, and delete in the next chapter. Chapter 3, Mastering Data Manipulation, CRUD Operations. With your bloglet form database schema now meticulously designed and deployed, it's time to bring it to life. A database without data is like an empty library, a great structure, but of no use until it's filled. This chapter is all about data manipulation language, DML, the set of SQL commands that allow you to interact with the data stored within your tables. The operations we'll cover are often collectively known by the acronym CRUD. Create, insert new data. Read, retrieve existing data. Update, modify existing data. Delete, remove existing data. Mastering these 4 fundamental operations is paramount for any developer interacting with a database. We'll populate our bloglet form database with some sample information and then learn how to query, modify, and remove it. 3.1 Inserting Data Insert. The insert statement is how you add new rows, records, into your tables. Let's begin by populating our bloglet form database. First, make sure you're connected to the bloglet form database. Use bloglet form, single row insertion. The most basic way to insert data is to specify the table name and the values for its columns. Imagine we want to add a new user to our users table. The users table has id, username, email, password hash, and created at columns. Since id is autoincrment and created at has a default currentmstmp, we typically don't need to specify values for them unless we want to override the defaults. Here's how to insert a user. Insert into users, username, email, password hash. Values, John Doe, john@example.com, hashed password John 123. After running this, a new row will be added to the users table. SQL statements usually don't provide a direct visual output confirmation of an insert beyond an OK or query executed successfully message. To confirm it, you would typically run a select query, which we'll cover next. If you omit the column names, you must provide values for all columns in the order they were defined when the table was created. This is generally not recommended as it makes your insert statements brittle if the table schema changes. However, for completeness, not recommended practice due to verbosity and brittle nature. Insert into users' values, null, Jane Smith, jane@example.com, hashed password Jane 456 default. In this less common form, null is used for the AUTOINCREMENT id column, allowing the database to assign a value, and default is used for created@ to trigger its default behavior. Multiple row insertion. You can insert multiple rows with a single insert statement, which can be more efficient than running individual insert statements, especially from application code. Separate each set of values with a comma. Let's add a couple more users and some categories. Insert into users, username, email, password hash values. Elisa developer, alice@example.com, Elisa hash 789. Bob writer, bob@example.com, bob hash 321. Insert into categories, name values. Technology, programming, lifestyle, travel, food. Now our users and categories tables have some data. Inserting from another select statement. Sometimes, you might want to populate a table with data that already exists in another table, or is the result of a query. You can do this by combining insert with select. For instance, imagine you had a temporary table of old users that you wanted to migrate. This approach is more common in database migration scripts or data warehousing. While we don't have an old users table, let's conceptually demonstrate how you might use this by inserting an existing user into a hypothetical archive_users table. Assuming an archive_users table exists with matching columns, create table archive_users like users to create a table with same structure. Insert into archive_users, id, username, email, password hash created@. Select id, username, email, password hash created@. From users, where username equals John Doe. This statement would select all columns for John Doe from the users table and insert them as a new row into the archive_users table. The column names must match or be explicitly ordered. Now, let's go ahead and insert some posts and comments using the users and categories we've already created. You might need to check the id values of users and categories you've inserted using a select statement, which we'll officially introduce in the next section, to ensure correct foreign key relationships. Let's assume John Doe has ID equals 1, Jane Smith ID equals 2, Elisa developer ID equals 3, and Bob writer ID equals 4. And technology is ID equals 1, programming is ID equals 2. Insert into posts, user id, title, content, status, values. 1. Introduction to SQL for beginners. This post covers the basics of SQL. Published. 3. Advanced Python techniques, exploring decorators, generators, and more. Published. 4. My journey to becoming a writer, from coding to storytelling, a new path. Draft. 1. Database normalization explained, a deep dive into 1NF, 2NF, and 3NF. Published. Insert into comments, posted, user id, content, values. 1-2, great intro, very clear and concise. 1-3, agreed, very helpful for new learners. 2-1, awesome concepts from Alice, thanks. 3-1, inspiring story, Bob. 4 null, as a guest, I found this normalization article very insightful. 4-2, still confusing, can you provide more examples? Insert into post categories, posted, category id values. Post 1 SQL is technology and programming. Select id from posts where title equals Introduction to SQL for beginners. Select id from categories where name equals technology. Select id from posts where title equals Introduction to SQL for beginners. Select id from categories where name equals programming. Post 2 Python is programming. Select id from posts where title equals Advanced Python techniques. Select id from categories where name equals programming. Post 3 Writing is lifestyle. Select id from posts where title equals My journey to becoming a writer. Select id from categories where name equals lifestyle. Post 4 Normalization is technology and programming. Select id from posts where title equals Database normalization explained. Select id from categories where name equals technology. Select id from posts where title equals Database normalization explained. Select id from categories where name equals programming. Note the embedded select statements in the post categories inserts. This is another way to illustrate insert. Select and ensures we use correct foreign key IDs dynamically rather than hard-coding. This approach is very common in migration scripts. 3.2 Retrieving data select. The select statement is by far the most frequently used DML command. It allows you to fetch data from your database. Basic select statements. To retrieve all columns from a table, use the asterisk. Select from users. Expected output concept. This query will return all rows and all columns from the user's table, showing the ID, username, email, password hash, and created at for each user you've inserted. You should see entries for John, Jane, Alice, and Bob. To retrieve specific columns, list them separated by commas. Select title, content from posts. Expected output concept. This will return only the title and content columns for every post in the posts table. Each row will represent one post. Filtering data with where clause. The where clause is used to specify criteria for filtering the rows returned by select, and update or delete. This is where you define the conditions for the data you want. Operators, equality equals, to find exact matches. Select username, email from users where username equals John Doe. Expected output concept. This will return a single row showing John Doe's username and email because username is an exact match for John Doe. Inequality, or to find rows that do not match a value. Select title from posts where status equals published. Expected output concept. This will list the titles of all posts that are not currently in published status, so you should see My Journey to Becoming a Writer. Comparison equals equals for numeric or date comparisons. Select title, publish edit from posts where publish edit 2023 to 1-1-0-0-0. Use current year as example. Expected output concept. This would return titles and publication dates for all posts published after the start of 2023. Given our sample data, this would likely include all published posts. Pattern matching, like used with wildcard characters. Percent matches any sequence of 0 or more characters. Matches any single character. Select username from users where username like J%. Find usernames starting with J. Expected output concept. This would return John Doe and Jane Smith. Select title from posts where title like %SQL%. Find posts with SQL anywhere in the title. Expected output concept. This would return Introduction to SQL for Beginners and Database Normalization Explained. Note that %value patterns are generally slower than those beginning with a literal character, as they cannot use an index efficiently. Range between. To check if a value falls within a specified range, inclusive. Select title, publish edit from posts, where publish edit between 2023 to 1-1-0-0-0 and 2023 to 12 to 31-23-59-59. Expected output concept returns posts published within the entire year 2023. List in to check if a value is present in a list of values. Select name from categories where name in technology, travel. Expected output concept. This would return technology and travel. Logical operators and or not to combine multiple conditions. Select title, status from posts where status equals draft and userid equals 4. Expected output concept. This finds posts that are both a draft and written by the user with ID equals 4 Bob Writer, so My Journey to Becoming a Writer should be returned. Select username, email from users where username equals John Doe or username equals Elisa Developer. Expected output concept. Returns the usernames and emails for John and Alice. Select title from posts where not status equals published. Expected output concept. Returns titles of posts whose status is not published, so My Journey to Becoming a Writer. Sorting results with order by. The order by clause sorts the result set based on one or more columns. ASC, ascending order default. Desk, descending order. Select title, publish edit from posts order by publish edit DESC. Expected output concept. Lists all posts, ordered from the most recently published to the oldest. Select username, created at from users order by username ASC. Expected output concept. Lists users alphabetically by username. You can sort by multiple columns. The sort happens by the first column, then by the second for rows with identical values in the first, and so on. Select posted, created at, content from comments order by posted ASC, created at DESC. Expected output concept. Returns comments, first grouped by posted in ascending order, and then for each posted, comments are sorted by created at in descending order, most recent comment for that post first. Limiting results with limit and offset. Limit constrains the number of rows returned, and offset specifies where to start. This is crucial for pagination in web applications. Select title from posts limit to. Expected output concept. Returns only the first 2 posts from the posts table. Order might not be deterministic without order by. Select title from posts order by publish edit ASC limit 1 offset 1. Expected output concept. Returns only the second oldest post title. Offset 1 skips the first row and limit 1 takes the next one. This is how you implement page 2 or page n of results. Using aliases for columns and tables. Aliases created using the as keyword, which is optional for columns but often enhances readability. Give a temporary name to a column or table in a query. Select username as username, email as user email from users. Expected output concept. Columns in the results set will be named username and user email instead of username and email. This is useful for making output more readable or matching application variable names. Table aliases are particularly useful in joins, covered in a later chapter, to make queries shorter and clearer, but can be used in any query. Select ptitle, ppublish edit from posts as p. Expected output concept. Same as select title, publish edit from posts, but p is now a shorthand for the posts table within this query. 3.3 Updating data update. The update statement is used to modify existing data in your tables. It's critical to use the where clause with update to prevent accidental modification of all rows. Update table name. Set column 1 equals value 1, column 2 equals value 2. Where condition, updating single rows. To update a single row, your where condition should identify a unique record, typically using its primary key. Let's say John Doe, user ID equals 1, wants to change his email. Update users. Set email equals johndonew@example.com. Where id equals 1, expected outcome. The email for the user with id of 1 will be changed. To verify, run select from users where id equals 1, updating multiple rows. If your where clause matches multiple rows, all matched rows will be updated. Suppose all draft posts should now be marked as archived. Update posts. Set status equals archived. Where status equals draft. Expected outcome. All posts with status equals draft, in our case, my journey to becoming a writer, will now have their status updated to archived. The update date column for these posts would also automatically reflect the current timestamp due to its on update currentTMESTMP definition. Using expressions in set. You can use expressions, functions, or even subqueries in the set clause. Let's assume comments older than a certain date should have a default user id of null. If they were created by a now-deleted user, we might want to flag them. For simplicity, let's just update all comments whose user id is currently null. Update comments. Set content equals concat guest comment, content, where user id is null, expected outcome. The single comment where user id is null from chapter 3.1 will have its content prefixed with guest comment. Caution: always test your update statements with a select containing the same where clause first to confirm you're targeting the correct rows before running the update. 3.4 Deleting data, delete. The delete statement is used to remove existing rows from a table. Just like update, the where clause is critical to prevent accidental data loss. Delete from table name where condition, deleting specific rows. To delete specific rows, provide a precise where condition. Let's remove the archived posts. Remember the on-delete cascade from posts to post categories and comments? This will auto-delete linked records in those tables. Delete from posts where status equals archived. Expected outcome: the post My Journey to Becoming a Writer will be removed. Due to the on-delete cascade foreign key rule, any entries in comments and post categories that refer to this post's ID would also be automatically deleted. If posted 3 was the only post Bob Writer had, then all comments related to that post, e.g., inspiring story Bob, will also be gone, deleting all rows. If you omit the where clause, delete will remove all rows from the table, but the table structure itself will remain. Delete from comments. Expected outcome. All comments from the comments table will be removed. The table structure, columns, indexes, constraints remains. If you then insert new comments, the AUTOINCREMENT primary key will resume from its last value, not reset to 1. Truncate table versus delete from, without WHERE. While delete from table removes all rows, truncate table achieves a similar visual result but operates differently and has distinct implications. Delete from table. DML command, it's a DML statement. Row by row, conceptually, it works like a traditional delete, potentially row by row, though optimized internally. Logging. Each deleted row is logged in the transaction log, making it slower for very large tables. Rollback can be rolled back if part of a transaction. Triggers, which we'll cover later, configured for delete events will fire. Auto increment, the AUTOINCREMENT counter is not reset. Truncate table, DDL command, it's a DDL statement despite appearing to manipulate data. Faster. It deallocates the data pages used by the table, which is much faster than delete for large tables. It's essentially dropping and recreating the table. Minimal logging. It typically generates much less transaction log entries. No rollback, cannot be rolled back. Once executed, the data is permanently gone. No triggers for delete events do not fire. Auto increment reset. The AUTOINCREMENT counter is reset to its starting value, usually 1. When to use which? Use delete from table where condition, for precise removal of specific rows. Use delete from table if you need to remove all rows, want delete triggers to fire, or need the operation to be part of a rollbackable transaction, even if it's slower. Use truncate table when you want to quickly empty a table completely, don't need rollback, don't need triggers, and want the AUTOINCREMENT counter reset. Be extremely careful with truncate in production environments. 3.5 Working with null values. Null in a database context doesn't mean 0, an empty string, or false. It means no value, unknown, or not applicable. Understanding how null behaves is essential for accurate queries. Understanding null. When a column is defined without a not null constraint, it can store null values. In our comments table, userid can be null for guest comments. Is null and is not null. You cannot use standard equality operators equals to check for null values. Instead, you use is null or is not null. Select id, content from comments where userid is null. Expected output concept. This will return the comments that were made by a guest, where userid is set to null. Select id, content from comments where userid is not null. Expected output concept. This will return all comments that were made by a registered user, where userid is assigned a value. Functions for handling null. Sometimes you want to substitute a meaningful value when a column is null. IFNULL, expression replacement value. If the expression is null, return replacement value, otherwise return the expression itself. Select id, if null userid, 0 as actual userid or guest. Content, from comments, expected output concept. For comments made by a guest, the actual userid or guest column will show 0 instead of null. For registered users, it will show their actual userid. Coalesce, expression 1, expression 2, expression n, returns the first non-null expression in the list. This is useful when you have multiple columns that might contain a value and you want to pick the first available one. Imagine BACUPML column exists, but for now we'll just demonstrate with hypothetical values. Select username, coalesce email, nomail provided at example.com as contact email. From users, expected output concept. This would show each user's username and their email. If an email was null, which it isn't in our users table due to its not null constraint, it would fall back to nomail provided at example.com. This function is more powerful when you have multiple fallback columns. 3.6 Basic aggregate functions. Aggregate functions perform a calculation on a set of rows and return a single summary value. They are often used with the group by clause, which we will cover in the next chapter, to summarize data for groups, but they can also operate on the entire result set. Count counts the number of rows or non-null values in a column. Count counts all rows, including those with null values. Select Count from Posts. Expected output concept. A single number representing the total count of posts in the posts table, which should be 3 after our previous delete. Count column name counts non-null values in a specified column. Select Count userid from comments. Expected output concept. A single number representing the number of comments linked to an actual user, i.e., userid is not null. Given our data, this would be fewer than the total number of comments. Count distinct column name counts the number of unique non-null values in a column. Select Count distinct userid from posts. Expected output concept. A single number showing how many unique users have written posts. Sum column name calculates the sum of a numeric column. Our tables don't have good numeric columns for sum. Let's imagine a post views column. Select Sum post views from posts. Expected output concept. A single number representing the total views across all posts if such a column existed. AVG column name calculates the average of a numeric column. Select AVG post views from posts. Expected output concept. A single number representing the average views per post. Min column name finds the minimum value in a column. Select Min publish edit from posts. Expected output concept. This would return the publication date of the oldest post max column name, finds the maximum value in a column. Select Max published at from posts. Expected output concept. This would return the publication date of the newest post. These aggregate functions are incredibly powerful for summarizing data, providing insights without needing to retrieve every single row. Summary of Chapter 3. You've just completed a crucial step in becoming a proficient MySQL developer. You've mastered the fundamentals of data manipulation language, DML, and now know how to perform the essential CRUD operations. Insert, effectively adding new records to your tables, whether individually or in batches. Select, retrieving data, using the powerful where clause for filtering, order by for sorting, and limit offset for pagination. Update, modifying existing records, emphasizing the importance of the where clause to target specific rows. Delete, removing records, understanding the precise control offered by where and the stark differences between delete from and truncate table. Null values, handling unknown data correctly with isNull, is not null, and utility functions like ifnull. Aggregate functions, getting summary insights from your data using count, sum, AVG, min, and max. In the next chapter, we'll build upon these foundational select skills to tackle more complex querying scenarios, including combining data from multiple tables using joins, working with subqueries, and grouping data for advanced aggregation. Your data is now alive. Let's learn to make it sing. Chapter 4, Advanced Querying, Joins, Subqueries, and Aggregates. In the previous chapter, you mastered the fundamental CRUD operations, learning how to insert, retrieve, update, and delete data within single tables. But the true power of relational databases, and a key skill for any developer, lies in combining, analyzing, and transforming data across multiple tables. This chapter delves into advanced SQL querying techniques that allow you to extract complex insights from your BlogPlatform database. We'll explore how to link related data using various types of joins, aggregate data into meaningful summaries using group by and having, and build sophisticated queries with subqueries, common table expressions, and modern window functions. By the end of this chapter, you'll be able to ask your database much more intricate questions. 4.1 Joining Tables, the Power of Relationships. The beauty of a relational database lies in its ability to break down information into distinct, manageable tables, normalization, and then reassemble that information when needed. This reassembly is done using join clauses. A join combines rows from 2 or more tables based on a related column between them, typically their primary and foreign keys. We'll use our BlogPlatform database schema for all examples. Remember, our posts table has a userid column that links it to the id column in the users table. This userid in posts is a foreign key. Inner join, retrieving matching rows. An inner join returns only the rows where there is a match in both tables based on the join condition. It's the most common type of join. Example 1. Displaying post titles with author usernames. We want to see the title of each blog post along with the username of the person who wrote it. Select P title, u.username. From, posts as P. Inner join, users as u, onp.userid equals uid. Explanation for audio. This query starts by selecting two specific columns, title from the posts table and username from the users table. The tables are given short aliases, P for posts and U for users, to make the query more concise. The inner join clause specifies that we are combining posts and users. The crucial part is the ON condition, p.userid equals uid. This instructs MySQL to link rows from posts to rows from users only when the userid in a post record exactly matches the id in a user record. Expected outcome: you would see a list where each row shows a post title and the author's username. Only posts that have a matching author in the users table will appear. If there were a post with a userid that didn't exist in the users table, that post would not be included in the result. Left join, left outer join, retrieving all rows from left table, matching from right. A left join, often called left outer join, the outer keyword is optional, returns all rows from the left table, the ones specified before left join, and the matching rows from the right table. If there's no match in the right table, the columns from the right table will appear as null. Example 2, displaying all users and their post titles, if any. We want a list of all registered users, and for each user, the titles of any posts they have written. Users who haven't written any posts should still be included in the list. Select u.username, p title, from, users as u. Left join, posts as p on uid equals p.userid. Explanation for audio. Here, users is the left table. The query selects the username from users and the title from posts. The left join on users and posts connects them where uid matches p.userid. Expected outcome: every username from the users table will be present. For users who have written posts, you'll see their username alongside each post title they authored. For users who have not written any posts, their username will appear, but the title column in that row will display null. This is very useful for finding authors who have not yet contributed. Right join, right outer join, retrieving all rows from right table, matching from left. A right join or right outer join is the mirror image of a left join. It returns all rows from the right table and the matching rows from the left table. If there's no match in the left table, columns from the left table will appear as null. Example 3. Displaying all categories and associated post titles, if any. We've set up categories. We want to see all categories and any posts assigned to them. A category should appear even if no posts are linked to it. Select c.name as category name, p title as post title. From, post categories as PC. Right join, categories as C on PC.categoryid equals C, id. Left join, we can chain joins. Here, linking post categories to posts. Posts as P on PC posted equals pid. Explanation for audio. This query starts by joining post categories, aliased as PC, with categories, aliased as C, using a right join. This ensures all categories records are included. The join condition is PC.categoryid equals CID. Then, it left joins the result of that with posts, aliased as P, on PC posted equals PID. Expected outcome: every category name will be listed. If a category has posts, their titles will appear alongside the category name. If a category currently has no associated posts, its category name will still be listed, but the post title column will be null. This is particularly useful for seeing which blog categories are currently unused. Full outer join, emulation in MySQL. A full outer join returns all rows when there is a match in either the left or the right table. It combines the results of a left join and a right join. MySQL does not have a direct full outer join keyword. However, you can emulate it by using union to combine the results of a left join and a right join. Example 4, all users and all posts, showing matches where they exist. Imagine we wanted to list every user and every post, matching them if the user is the author, but still listing users without posts and posts without authors, if that were possible in our schema. Left join part, all users and their posts. Select u.username, p title. From users as you left join posts, as p on uid equals p dot userid. Union. Right join part. All posts and their authors, including posts without authors if userid was nullable. In our schema, posts always have a userid, so the right join here would essentially be an inner join. For a true full outer example, consider tables where both sides could have unmatched records. Select u.username, p-title. From users as you right join posts, as p on uid equals p.userid. Where uid is null. This where clause filters for records only found in the right table. Explanation for audio. This query is composed of two select statements combined by union. The first select performs a left join from users to posts, giving us all users and their associated posts, with null for post titles if no match. The second select performs a right join from users to posts. But crucially, it includes a where uid is null clause to only capture posts that don't have an author, if our schema allowed for null userid in posts. Using union, which removes duplicates, effectively merges these two sets to simulate a full outer join. Expected outcome, you would see a list of all usernames and all post titles. Where a user is an author, their username and post title will align. Users who haven't written posts will appear with null in the post title column. Posts that might exist without an author, if allowed by the schema, would appear with null in the username column. Cross-join, Cartesian product. A cross-join creates a Cartesian product of the two tables. This means every row from the first table is combined with every row from the second table. This generally produces a very large result set and is rarely used unless you explicitly need to generate all possible combinations. Example 5. All possible combinations of users and categories. This is a purely illustrative example, as it doesn't have a practical use in our blog application. Select u.username, c.name as category name. From users as u. Cross-join, categories as c. Explanation for audio. This query combines every row from the users table with every row from the categories table. Expected outcome. If you have 4 users and 5 categories, the result set would have 20 rows, 4, 5, showing every user paired with every category. Self-joins. A self-join is when a table is joined with itself. This is useful when you have hierarchical data within a single table, such as an employees table where an employeeid and a managerid, which references another employeeid in the same table, exist. Our BlogPlatform database doesn't have a direct hierarchical structure like this, but we can illustrate the concept with another common scenario, finding duplicates or related items within the same table. Example 6. Finding comment pairs from the same user on the same post. This is a more complex example, but demonstrates the idea. If someone comments multiple times on the same post, select c1.content as comment 1, c2.content as comment 2, u.username as commenter. From comments as c1, inner join, comments as c2 on c1, posted equals c2, posted and c1.userid equals c2.userid, and c1 id c2 id. Inner join, users as uonc, 1.userid equals uid. Explanation for audio. This query joins the comments table with itself, aliasing it as c1 and c2. The join conditions are c1, posted equals c2, posted, meaning both comments are on the same post, c1.userid equals c2.userid, meaning both comments are by the same user, and c1 id c2 id to avoid duplicating pairs and comparing a comment to itself. Finally, it joins with the user's table to get the common commenter's username. Expected outcome. If a user has made more than one comment on the same post, this query will return pairs of those comments along with the commenter's username. This helps in identifying users who leave multiple comments on the same article. Understanding on versus using. When performing joins, you specify the join condition using either on or using. On clause. The most flexible method. You specify the full columns for comparison, even if they have different names. Inner join table 2 on table 1 dot columna equals table 2 dot column. This is the standard and recommended way, as it's explicit and works even when columns don't share the exact same names. Using clause, a shorthand method to use when the columns you're joining on have the exact same name in both tables. Inner join table 2 using common column name. For example, if both users and posts tables had a column named created buserid, you could use on posts created buserid users created buserid, or using created buserid. We used onp.userid equals uid because userid in posts is not the same name as id in users. 4.2 Grouping data with group by and having. While aggregate functions, like count, sum, avg, summarize data for an entire result set, the group by clause allows you to divide the rows into groups and then apply aggregate functions to each group separately. The having clause then filters these groups, grouping with group by. The group by clause is used to group rows that have the same values in specified columns into a summary row. Example 7. Counting the number of posts per user. We want to know how many posts each user has written. Select u.username. Count PID as post count. From users as u. Left join, use left join to include users with 0 posts. Posts as p on uid equals p.userid. Group by u.username. Explanation for audio. This query aims to count posts for each user. It first performs a left join from users to posts to ensure all users are included, even those without posts. Then, the group by u.username clause groups all rows that share the same u.username into a single logical group. The count PID aggregate function then counts the number of posts PID within each of these groups, and the result is aliased as post count. Expected outcome. The result will be a list where each row contains a username and the total number of posts that user has written. For users with no posts, their post count will be 0. Example 8. Counting comments per post and user. This example will show how to group by multiple criteria. Select ptitle as post title, u.username as commenter username, count cid as comment count. From comments as c. Inner join. Posts as p on c posted equals pid. Left join. Users as u onc.userid equals uid use left join since userid can be null. Group by ptitle u.username. Order by comment count desc. Explanation for audio. This query joins comments with posts and users to get titles and usernames. The group by ptitle u.username clause groups the comments by both the specific post they belong to and the user who wrote them. The count CID then tallies the comments for each unique combination of post and commenter. The results are ordered to show the most active comment pairs first. Expected outcome. A list showing post titles, the username of the commenter, and the number of comments that specific user made on that specific post. If a comment was anonymous, userid is null, the commenter username will appear as null. Filtering with having. The where clause filters individual rows before they are grouped. The having clause filters groups after they have been aggregated by group by. You cannot use aggregate functions directly in the where clause. They must be in having. Example 9. Finding users with more than one post. Building on example 7, we now only want to see users who have written more than one post. Select u.username. Count PID as post count. From users as u. Inner join, using inner join here, because we only care about users who have posts. Posts as p on uid equals p.userid. Group by u.username. Having count PID 1. Explanation for audio. This query first finds post counts per user, similar to example 7, but crucially uses an inner join as users with 0 posts would never meet the having condition. The having count PID 1 clause then filters these groups, keeping only those where the calculated post count, the aggregate result for that group, is greater than 1. Expected outcome. Only usernames of users who have authored more than one post will be listed, along with their respective post counts. 4.3 Subqueries, queries within queries. A subquery, or inner query, is a select statement nested inside another SQL query. Subqueries can be used in select, from, where, having clauses, or even with insert, update, and delete statements. Scalar subqueries. A scalar subquery returns a single value, one column, one row. They can be used anywhere a single value expression is expected. Example 10. Finding posts published after the oldest post by a specific user. Let's find all posts published after John Doe's. User with ID equals 1, oldest post. Select title, publish edit. From posts, where publish edit, select min publish edit. From posts, where userid equals 1. Explanation for audio. The inner select query select min publish edit from posts where userid equals 1 first executes. This subquery identifies the earliest publication date for any post authored by user ID 1 and returns that single date value. The outer query then uses this single date value in its where clause to find all other posts published later than that date. Expected outcome: a list of post titles and their publication dates that are more recent than John Doe's oldest post. Row subqueries. A row subquery returns a single row, but can contain multiple columns. They are often used for comparison with another row. Example 11, finding the user who wrote the most recent post. This is a bit contrived for a row subquery, but illustrates the principle. Select username. From users, where id equals, select userid from posts order by publish edit DESC limit 1. Explanation for audio. The inner subquery select userid from posts order by publish edit DESC limit 1 finds the userid of the most recently published post. The outer query then retrieves the username for that specific userid. Expected outcome: the username of the author who created the most recent blog post. Column subqueries. A column subquery returns a single column, but can contain multiple rows. They are often used with in, any, all operators. Example 12, finding users who have not written any posts. We can use a subquery with not in. Select username. From users, where id not in, select distinct userid from posts. Explanation for audio. The inner subquery select distinct userid from posts returns a list of unique user IDs who have written posts. The outer query then selects usernames from the users table where their id is not in that list of post authors. Expected outcome: a list of usernames for users who have not yet published any blog posts. Invis EXISDS with subqueries. While IN and EXISDS can often achieve similar results, their performance characteristics and best use cases differ. In evaluates the subquery first, creates a list, then checks if the outer query's value is in that list. It performs well when the subquery list is relatively small. EXISDS checks for the existence of any row returned by the subquery. The subquery is often correlated, meaning it references a column from the outer query. EXISDS is generally more efficient when the subquery might return a very large number of rows, as it stops processing as soon as it finds the first match. Example 13, finding posts with comments using EXISDS. Select title, from posts as p, where EXISDS, select one from comments as c where c posted equals pid. Explanation for audio. For each post in the outer query, the EXISDS subquery checks if there is at least one comment where the comments posted matches the post's id. As soon as one such comment is found, the subquery stops, and EXISDS returns true for that post. Expected outcome: a list of titles for all posts that have at least one comment. Correlated subqueries. A correlated subquery is a subquery that depends on the outer query for its values. It executes once for each row processed by the outer query. While sometimes necessary, they can be less performant than joins or non-correlated subqueries, especially on large datasets. Example 14, finding users whose latest comment was on their own post. This assumes a userid in comments and post-userid are both valid. Select u.username. From users as u, where select c posted from comments as c where c.userid equals uid order by c created at DESC limit 1 in. Select pid from posts as p where p.userid equals uid. Explanation for audio. This query starts by iterating through each user in the outer users table. For each user, the first subquery finds the posted of the most recent comment made by that specific user. The second subquery finds all posteds of posts authored by that same specific user. The where clause then checks if the post ID from their latest comment is among the post IDs they authored. This subquery is correlated because the inner queries, where c.userid equals uid and where p.userid equals uid, Refer back to the UID from the outer query. Expected outcome. A list of usernames where the user's most recent comment was posted on one of their own blog posts. 4.4 Common Table Expressions, CTEs. Common Table Expressions, CTEs, introduced with the with clause, allow you to define a temporary named result set that you can reference within a single select, insert, update, or delete statement. They don't store data permanently, but improve query readability and modularity, especially for complex, multi-step queries that might otherwise involve many nested subqueries. Example 15. Finding users with posts and their comment counts using CTEs. Let's first find all users who have published posts, and then count all comments on those posts. With published posts as, select it as posted, userid title. From posts, where status equals published, user post comment counts as, select pp.userid, pp title as post title, count CID as comment count. From, published posts as pp, left join, comments as C on pp posted equals C posted. Group by, pp.userid, pp title. Select, u.username, up post title, up.comment count. From, users as u. Inner join, user post comment counts, as up on uid equals up.userid. Order by, u.username, up post title. Explanation for audio. This query uses two CTEs. Published posts. This first with block defines a temporary result set named published posts. It selects the id, userid, and title from the posts table, filtering for posts with a published status. User post comment counts. This second with block is defined after a comma and references the published posts CTE. It takes those published posts, left joins them with comments to count comments for each published post. Finally, the main select statement then joins the user's table with the user post comment count CTE to display the username, post title, and comment count for each published post. Expected outcome. A list showing the username of authors, their published post titles, and the number of comments each of those posts has received. This demonstrates how complex logic can be broken down into more readable, sequential steps. 4.5 Window Functions, MySQL 8.0 Plus. Window functions perform calculations across a set of table rows that are related to the current row. Unlike aggregate functions that reduce the number of rows, e.g., count returns one row per group, window functions return a value for each row in the result set. They are often used for ranking, moving averages, or cumulative sums. They require MySQL 8.0 or newer. The magic keyword for window functions is over. Common analytical functions, ROWNUMBER, assigns a unique sequential integer to each row within its partition, starting from 1. Rank assigns a rank to each row within its partition. If rows tie, they get the same rank, and the next rank skips values, D and SRNK. Similar to rank, but if rows tie, the next rank does not skip values. Example 16, ranking comments within each post by creation date. We want to see all comments and their rank within each post, e.g., the first, second, third comment on a given post. Select, posted, userid, content, created at, ROWNUMBER, over partition by posted order by created at ASC, as comment rank. From, comments, order by, posted comment rank, explanation for audio. This query selects comment details. The ROWNUMBER is applied as a window function. Partition by posted divides the data into separate groups for each posted. Order by created at ASC specifies that within each posted group, comments should be ranked by their created at timestamp in ascending order. Comment rank is the alias for the resulting rank. Expected outcome. A list of all comments, where each comment has an additional column comment rank indicating its order of appearance, based on creation time, within the specific post it belongs to. Aggregate window functions. You can also use aggregate functions as window functions. They will calculate the aggregate value for the window, or partition, but still return it for every row in that window. Example 17. Displaying each comment with the total comment count for its post. Select C.content, C created at, P title as post title, count CID over partition by C posted, as total comments on this post. From, Comments as C. Inner join. Posts as P on C posted equals PID. Order by. C posted, C created at. Explanation for audio. This query selects comment content, creation time, and the title of its associated post. The count, CID, over partition by C posted part calculates the total number of comments, count CID, for each specific posted partition by C posted. Critically, this total comments on this post value is returned for every row belonging to that post's partition, instead of collapsing to a single summary row per post like a group BY would. Expected outcome. A list of all comments, where each comment row also includes the total count of comments for the post it belongs to. 4.6 Set operations. Set operations combine the results of two or more select statements into a single result set. The columns in each select statement must be compatible, same number of columns, and corresponding columns must have compatible data types. Union and union all. Union combines the result sets of two or more select statements and removes duplicate rows. Union all combines the result sets of two or more select statements and retains all duplicate rows. Union all is generally faster because it doesn't perform the overhead of checking and removing duplicates. Example 18. Listing all usernames and all category names in a single column. A practical data type compatibility example. Select username as item name from users. Union all. Select name as item name from categories. Order by item name. Ordering applied to the final combined result set. Explanation for audio. This query combines two distinct select statements. The first one selects all usernames from the users table, aliasing the column as item name. The second selects all names from the categories table, also aliasing the column as item name. The union all operator merges these two result sets, including any duplicates if they existed, though unlikely here. Finally, order by item name sorts the combined list. Expected outcome. A single list containing all usernames and all category names, sorted alphabetically. Each name will appear exactly as many times as it exists in its respective source table. If you used union instead of union all, any identical usernames and category names would appear only once. Intersection and difference, emulation in MySQL. MySQL does not have direct intersect or except or minus operators. You can emulate these using join along with where exists or where not exists, or subqueries with in or not in. Example 19. Emulating intersect finding users who are both authors and commenters with an ID and username. This is a bit more involved to illustrate. We want to find the IDs and usernames of users who have both written posts and made comments. Select UID, u.username. From users as u. Where UID in, select distinct userid from posts where userid is not null. And UID in, select distinct userid from comments where userid is not null. Explanation for audio. This query finds users whose ID is present in the list of distinct userids from the posts table, meaning they authored a post, and whose ID is also present in the list of distinct userids from the comments table, meaning they made a comment. This effectively finds the intersection of the two sets of users. Expected outcome. A list of user IDs and usernames for individuals who have both written posts and made comments on the blog. 4.7 Advanced String and Date Functions. MySQL provides a rich set of built-in functions to manipulate strings, numbers, and dates within your select statements. Here are a couple of useful ones for developers. String functions. Concat string 1, string 2 concatenates joins two or more strings together. Substring string start length extracts a substring from a string. Length string returns the length of a string. Lower string, upper string converts a string to lowercase or uppercase. Example 20, displaying user information in a formatted way. Select id, concat username, email, as userinfo. From users, explanation for audio. This query selects the user id and then uses the concat function to combine the username, an opening parenthesis, the email, and a closing parenthesis into a single userinfo column. Expected outcome. Each row will show the user's ID and then a formatted string like John at example.com. Date and time functions. Date format formats a date value according to a specified format string. Now, returns the current date and time. CURDATE returns the current date. DateDiff date1, date2 returns the number of days between two dates. DateAdd date interval value unit, DateSub date interval value unit. Adds or subtracts time intervals from dates. Example 21, formatting post-publication dates and calculating age. Select title, date format publish edit, %m%d, %y as formatted publish date. Date diff cur date, publish edit as dasen published. From posts, explanation for audio, this query selects the post title. For formatted publish date, it uses DATFORMAT to display publish edit in a more readable format, like January 1st, 2023. For dasen published, it calculates the difference in days between the current date, CURDATE, and the publish edit date for each post. Expected outcome: a list of post titles, their publication dates formatted nicely, and the number of days that have passed since each post was published. Summary of Chapter 4. You've significantly expanded your SQL querying toolkit. You are no longer limited to simple data retrieval from single tables. You can now craft powerful, precise queries that leverage the relational nature of your data. You've learned about joins, inner, left, right, cross, and self joins, understanding how to combine data from multiple tables based on logical relationships, and the subtle differences in their results. Group by and having, summarizing and filtering aggregated data to gain insights into groups of records. Subqueries, nesting select statements to solve more complex problems where one query's result feeds into another. Common table expressions, CTEs, structuring complex queries for better readability and maintainability using the with clause. Window functions, MySQL 8.0+, performing sophisticated analytical calculations like ranking and running totals without aggregating rows into a single summary. Set operations, combining results from different queries using union and union all. Advanced functions, harnessing built-in string and date functions to transform and present data. This mastery of advanced querying forms the backbone of any data-driven application. In the next chapter, we'll turn our attention to one of the most critical aspects of database performance, indexing. You'll learn how indexes can dramatically speed up the very queries you've just learned to write. Chapter 5. Indexes, the key to faster queries. You've learned how to craft sophisticated queries to extract exactly the data you need. However, writing a correct query is only half the battle. A slow query can cripple an application, leading to frustrated users and overloaded servers. The secret weapon for dramatically improving query performance in relational databases is indexing. Imagine a database with millions of records. Without indexes, every time you search for a specific piece of data, the database might have to scan through every single row, one by one, to find what you're looking for. This is like trying to find a specific word in an enormous book without an index or page numbers. You'd have to read the entire thing. In this chapter, we'll dive deep into indexes, what they are, how they work, the different types available in MySQL, and most importantly, how to use them effectively to make your queries run at lightning speed. 5.1. What are indexes and why do we need them? Let's start with an analogy everyone can understand, a book. Analogy, the book index. When you want to find information about a specific topic in a nonfiction book, you don't typically read the entire book from cover to cover. Instead, you turn to the index at the back. The index lists keywords or topics alphabetically and, crucially, provides page numbers where those topics can be found. You quickly locate the keyword, see the page numbers, and jump directly to the relevant sections. This is much faster than flipping through every page. A database index works in a very similar way. It's a special lookup table that the database search engine can use to speed up data retrieval. How indexes improve select performance. When you create an index on one or more columns of a table, MySQL builds a sorted structure, typically a B-tree, a type of self-balancing tree data structure, containing the values from those columns and pointers to the actual rows where the data resides. When you then execute a select query with a where clause that references an indexed column, MySQL can use the index to quickly locate rows. Instead of scanning all rows in the table, a full table scan, MySQL traverses the smaller, sorted index structure to find the relevant data pointers. This is incredibly fast, especially for large tables. Order results efficiently. If your query includes an order by clause and the columns in the order by match and index, MySQL can often read the data already in the sorted order of the index, avoiding an expensive sorting operation. Speed up joins. Indexes on columns used in join conditions can significantly accelerate the process of matching rows between tables. Trade-offs: the cost of indexing. While indexes are a boon for select queries, they come with certain costs. Storage space. Indexes themselves take up disk space. A large number of indexes, or indexes on very large text columns, can consume significant storage. Write performance. Every time you insert, update, or delete a row in a table that has indexes, MySQL must also update or modify the corresponding index structures. This adds overhead to write operations. Too many indexes can slow down your application's write-intensive tasks. Memory usage. Indexes are often loaded into memory, specifically the InnoDB buffer pool, to provide faster access. More indexes mean more memory consumed. The art of effective indexing is to find the right balance: enough indexes to make your reads fast, but not so many that your writes become unacceptably slow or your storage memory requirements explode. 5.2 Types of indexes. MySQL supports various types of indexes, each suited for different use cases. In modern MySQL, most tables use the InnoDB storage engine, which handles indexes somewhat differently from older engines like MyISAM. Primary key indexes, clustered index for InnoDB. Primary key equals index. When you define a primary key on a column or set of columns, MySQL automatically creates an index on these columns. Clustered index. For InnoDB tables, the primary key index is special. It's a clustered index. This means the actual data rows of the table are physically stored on disk in the order of the primary key. This makes retrieving data by primary key exceptionally fast. Uniqueness and not null. By definition, primary keys must contain unique and non-null values. Example: in our users table, id.int.autoincrement primary key automatically creates a clustered index on the id column. Secondary indexes, non-clustered. Definition: any index that is not the primary key is a secondary index, also known as a non-clustered index. How they work in InnoDB. A secondary index contains the indexed column's value and a pointer to the primary key value of the row. To retrieve the full row, MySQL first uses the secondary index to find the primary key, and then uses the clustered index, the primary key structure, to locate the actual data row. This two-step lookup is generally efficient. Uniqueness can be unique or non-unique. Example: an index on username or email in the users table would be a secondary index. Unique indexes. Purpose: a unique index ensures that all values in the indexed columns are unique. It functions as both a performance enhancer and a constraint. Implicitly unique: a primary key is a special type of unique index. Constraint: if you define a unique constraint on a column, MySQL automatically creates a unique index on that column. Example: in our users table, username varchar 50, not null unique implicitly creates a unique secondary index on the username column, in addition to enforcing uniqueness. Multi-column, composite indexes. Definition: an index created on more than one column. The order of columns in the index definition is crucial. Leftmost prefix rule. A composite index, Kale, Kalbi, Kalsi, can be used efficiently for queries that filter on Kale, or Kale, Kalbi, or Kale, Kalbi, Kalsi. It cannot be used directly for queries that only filter on Kalbi or Kalsi alone. Example: for our post categories table, we have a composite primary key, posted, categoryed. This acts as a composite index. Queries filtering by posted or by both posted and categoryed will benefit from this index. Full-text indexes, briefly. Purpose: designed for efficient text searches using natural language processing, NLP, capabilities, such as finding words within large text blocks, text, or VARCHAR. Limitations: uses a different indexing algorithm, inverted index, than B-trees. More complex to configure and less flexible than external search solutions, Elasticsearch Solr only applies to char text columns. Example, if you wanted to allow complex keyword searches within the content column of the posts table, a fulltext index would be a candidate. Spatial indexes, briefly. Purpose: used for geographic data stored in GIS, Geographic Information System. Functions, such as points, lines, and polygons, require spatial data types. Niche use: not typically relevant for most general web applications, unless dealing with location-based services significantly. 5.3 Creating and dropping indexes. You can explicitly create and drop secondary indexes using createIndex or alter table. Primary keys and unique indexes are created implicitly when you define their corresponding constraints in your create table or alter table statements. Create index syntax. You can add an index to an existing table using createIndex. Create index name on table name, column name, and a curriculum. Example, creating an index on userid in posts for faster lookups by author. Create index suserid on posts, userid. Explanation for audio. This command creates a new index named suserid on the posts table, specifically on the userid column. Alter table add index drop index. The alter table statement is generally preferred for managing indexes, as it keeps index management operations consistent with other schema modifications. Adding an index. Alter table name add index name, column name, and a curriculum. Example, adding an index to email in comments if we frequently search for comments by email. Alter table comments add index userid. Explanation for audio. This alter table statement adds an index on the userid column of the comments table, specifically naming the index userid. Dropping an index. Alter table name drop index name. Example, dropping the userid index if it's no longer needed. Alter table posts drop index userid. Explanation for audio. This alter table statement removes the index named userid from the posts table. Note that you drop an index by its name, not the column it's on. You can find index names using show index from table name. Implicit indexes. As mentioned, primary key and unique constraints automatically create indexes. You don't explicitly run createIndex for them. Example, create table authors. id primary key. Email varchar 255 unique. Name varchar 100. This single create table statement automatically creates a clustered primary key index on id, a unique secondary index on email. 5.4 How MySQL uses indexes. Understanding how MySQL's query optimizer decides to use or not use an index is key to effective performance tuning. The explain statement, covered in detail in the next chapter, is your window into this process. When you run a select query, MySQL's optimizer tries to find the most efficient way to retrieve the data. It considers available indexes. Here are common type values you might see in explain output that indicate how an index is being used. All full table scan. This is the worst case. MySQL has to read every single row in the table to find the matching ones. This happens when no suitable index is available or the optimizer determines that a full table scan is faster, e.g., for very small tables, or when retrieving a very large percentage of rows. Index, full index scan. MySQL reads the entire index from beginning to end. This is better than a full table scan if the index is much smaller than the table itself, or if the query can be satisfied entirely by the index, a covering index. Range, index range scan. This is very good. MySQL uses an index to retrieve rows within a specified range, e.g., where created at between 2023 to 1 and 2023 to 1 to 31. It quickly finds the start of the range in the index and reads sequentially until the end, performing an efficient lookup. Ref, non-unique index lookup. This is an efficient lookup by a specific values in a non-unique index. It's often seen in join operations. MySQL quickly finds the first match and then efficiently scans forward for other matches. ecref, unique index lookup for joins. This is excellent. It happens when joining with a unique index, like a primary key or unique key, on the second table in the join. For each row in the first table, MySQL expects to find exactly one matching row using the unique index. This is very fast. Const/system, optimizer constants, the best possible. MySQL has reduced the table to 0 or 1 row at compile time. This typically happens when filtering on a primary key with an equality comparison equals. Covering indexes. A covering index is an index that includes all the columns required by a query, meaning MySQL can return all the requested data directly from the index itself, without needing to go to the actual data rows of the table. Example, if you have an index on userid, status in the posts table, and you run. Select userid, status from posts where userid equals 123. MySQL can satisfy this query directly from the index. It doesn't need to visit the main posts table, which is very fast. Index merge optimization, brief mention. In some cases, MySQL can use multiple indexes for a single query, e.g., if you have where call A equals X and call B equals Y and separate indexes on call A and call B. The optimizer will fetch row IDs from both indexes and merge the results. This is less common, and the optimizer might prefer a composite index if available. 5.5. Choosing the right columns for indexing. This is where the practical art of indexing comes in. Not all columns are good candidates for indexing, and not all indexes are equally beneficial. Columns in where clauses. Rule. If a column is frequently used in a where clause, e.g., where username equals John Doe, where publish edit 2023 to 1:1, it's a strong candidate for an index. High cardinality. Indexes are most effective on columns with high cardinality, meaning many unique values. Examples: email, username, id low cardinality. Indexes on columns with low cardinality, few unique values, are less effective. Example: a gender column, only 2 values, M, F. For such columns, a full table scan can sometimes be faster than traversing an index that points to a large percentage of the rows. However, if a low cardinality column is combined with other columns in a composite index, it can still be useful. Columns in order by and group by clauses. Rule. Indexes can help avoid expensive sorting, file sort, and grouping operations. If your queries often sort or group by a specific column or set of columns, consider indexing them. Match order. For composite indexes, the order of columns in order by should match the index's column order for maximum benefit. Columns in join conditions. Rule. Columns used in ON clauses for join operations, especially foreign keys, are excellent candidates for indexes. Columns for covering indexes. Rule. If your query only needs a few columns, and those columns are all part of an existing index, either a composite index or a clustered index where the primary key is used to find everything, it can be incredibly fast. Consider creating composite indexes that cover common queries. Prefix indexing. For varchar or text columns, indexing the entire column might lead to very large indexes and slow down write operations. If you only need to match on the beginning of a string, e.g., where email like %, you can create a prefix index using only the first n characters of the column. Create index email prefix on users, email 10, indexes only the first 10 characters of email. This saves space and can still be effective for initial character matching. 5.6. Common indexing pitfalls and best practices. Avoiding common mistakes can save you a lot of headache down the line. Pitfall 1. Over-indexing versus under-indexing. Over-indexing. Too many indexes slow down writes and consume excessive disk space. Every index has a cost. Under-indexing. Not enough indexes leads to slow select queries and potentially full table scans. Best practice. Add indexes incrementally based on identified performance problems. Use Explain, Chapter 6, to analyze slow queries and determine if an index would help. A general rule is to start with indexes on primary keys, unique keys, and foreign keys. Pitfall 2. Using like %value, leading wildcard. Problem: queries like where name like %John%, where the wildcard is at the beginning of the pattern, cannot use a standard B-tree index efficiently because the index is sorted by the beginning of the string. MySQL falls back to a full table scan. Best practice: avoid leading wildcards if performance is critical for large datasets. Consider FULLTEXT indexes or external search engines if you need robust, contains, or fuzzy search capabilities. Pitfall 3: using functions on indexed columns. Problem: applying a function to an indexed column in a where clause, where year created at equals 2023, makes the index unusable, as MySQL needs to calculate the function's result for every row before it can compare. Best practice: rewrite queries to avoid functions on the indexed column itself. Instead of year created at equals 2023, use created at between 2023 to 1 to 1 and 2023 to 12 to 31 23 59 59. Pitfall 4: misunderstanding composite index order. Problem: building a composite index colB, but then querying where colB equals value. This might not use the index efficiently or at all because call is the leftmost prefix. Best practice: design composite indexes based on query patterns. If you frequently query by call alone or call and callb, then callb is good. If you often query by callb alone, you also need a separate index on callb. Pitfall 5: not considering data volume. Problem: indexes on small tables, a few hundred or thousand rows, might not provide significant performance benefits, and the overhead might not be worth it. Best practice: focus indexing efforts on large tables, tens of thousands to millions of rows, where a full table scan is truly a bottleneck. Maintenance of indexes in NoDB. For InnoDB tables, indexes generally require minimal manual maintenance. InnoDB is self-balancing, so reindexing to combat fragmentation is rarely necessary. The optimizer automatically chooses which indexes to use. You don't need to manually enable or disable them based on a query. Summary of Chapter 5. Indexes are the unsung heroes of fast database performance. You've learned that they are specialized data structures that dramatically speed up data retrieval operations, like select and join, much like a book's index helps you quickly find information. You now understand the fundamental concept of how indexes work and their vital role in database performance. The trade-offs involved: faster reads at the cost of increased storage and slower writes. The different types of indexes in MySQL, including clustered, primary key, and secondary, unique, and composite indexes. How to create and drop indexes using create index and alter table. The basics of how MySQL's optimizer uses indexes, including the extremely efficient covering index scenario. Key strategies for choosing columns to index, focusing on WHERE, order by, group by, and join clauses, and the importance of cardinality. Common indexing pitfalls, such as the like percent value, anti-pattern, and function use on indexed columns, and how to avoid them. Equipped with this knowledge, you are ready to proactively build performance schemas. In the next chapter, we'll dive deeper into performance tuning, using tools like Explain to diagnose slow queries and apply your indexing knowledge to solve real-world performance issues. This is where theory meets practice. Chapter 6, Performance Tuning, Diagnosing and Optimizing Queries. You're a skilled MySQL user now. You can design effective schemas, master CRUD operations, craft complex queries with joins and subqueries, and understand the core concepts of indexing. But what happens when your perfectly crafted query still takes too long to run, or your application users complain about slow loading times? This chapter is dedicated to query performance tuning. It's where the art and science of database development truly shine. You'll learn how to identify bottlenecks, analyze how MySQL executes your queries, and apply optimization techniques to make your applications responsive and scalable. While full-stack DBA-level tuning is a deep subject, as a developer, you have significant power to optimize the queries and schema interacting with your application. 6.1. The Query Optimization Process. Optimizing database queries is often an iterative process. It generally follows these steps: identify slow queries, determine which queries are taking too much time, analyze query execution, understand how MySQL is executing the query, its execution plan, often using the explain statement. Optimize. Based on the analysis, make changes to the query, add modify indexes, or adjust schema. Verify. Test the optimized query to confirm performance improvement. Let's dive into the tools and techniques for each step. 6.2. Using explain to understand query execution. The explain statement is your most powerful friend when it comes to understanding and optimizing SQL queries. It provides a detailed execution plan for a select, and sometimes insert, update, delete statement, showing you how MySQL joins tables, which indexes it uses, and how much work it expects to do. To use explain, simply prefix your select query with the explain keyword. Explain select u.username, p-title. From users u enter join posts p, on uid equals p.userid, where u.username equals John Doe. Interpretation of explain output. The output of explain is a table with several columns. While some columns are dense with information, understanding a few key ones can tell you a lot about your query's performance. Let's assume an example output for our query to illustrate. Id select type table partitions, type possible keys key keylin ref rows, filtered extra. 1 simple u null const primary. Username primary, 4 const 100.00, using index. 1 simple p null ref ixposuserid 4 uid 3 100.00, using where. Let's break down the most important columns. Id, a unique identifier for each select in the query. For complex queries with subqueries or unions, you might see multiple id select type, the type of select query. Simple, a simple select, no union subqueries. Primary, the outermost select in a union or complex query. Subquery, the first select in a subquery. Derived, a select from a derived table, e.g., a subquery in the FROM clause. Table, the table referenced in this row of the execution plan. Type, this is one of the most important columns. It indicates how MySQL accesses rows from the table. Ordered from best to worst, const, system, excellent. Table has at most one matching row, retrieved very quickly. Occurs when querying a primary key or unique index with constants. Ecref, excellent for joins. One row is read from this table for each combination of rows from previous tables. Used for joins, where you reference a primary key or unique index in the join table. Ref, good. All rows matching a reference value are retrieved. Used for joins on non-unique indexes or when referring to part of a composite index. Range, good. Rows are retrieved within a range of values using an index. Used for where clauses with between, like prefix %. Index, fair. Full index scan, all rows in the index are read. Better than all if the index is smaller than the table or if it's a covering index. All bad, full table scan. Every row in the table is read to find matching rows. This is generally a performance bottleneck for large tables. Possible keys indicates which indexes MySQL could use to find rows for this table. Key, the actual index that MySQL chose to use. If null, no index was used. Keylin, the length of the key in bytes that MySQL decided to use. A shorter keylin usually means a more restrictive filter. Ref, shows which columns or constants are used with the key to select rows. Const means a constant value, e.g., John Doe. Func means a function. db.table.column means a column from another table, common in joins. Rows, another very important column. An estimate of the number of rows MySQL must examine to execute the query. A lower number is better. For all, this will be the total number of rows in the table. Filtered, an estimate, as a percentage, of the rows filtered by the table condition. A higher percentage means more rows are being eliminated at an early stage. Extra provides additional important information about how MySQL executes the query. Using index, excellent. All data needed comes directly from the index, covering index. No need to access the table data. Using where, a where clause is applied. Often appears with a type other than all, range, const, ecref, meaning some filtering occurs after data is retrieved. Using filesort, bad. MySQL needs to do an extra pass to sort the data, e.g., for order by or group by, because no suitable index was found or used. This is an expensive operation for large datasets. Using temporary, bad. MySQL needs to create a temporary table to process the query, often for group by or distinct operations that cannot be optimized by indexes. This is slow, especially if the temporary table exceeds memory and needs to be written to disk. Using index condition. Good. MySQL is using part of the index to filter data before accessing the full row, especially useful for range conditions or like prefix %. Diagnosing common problems with explain. Type, all, indicates a full table scan. Rectify by adding an index on relevant columns in the where, join, or order by clauses. Extra, using file sort. A clear sign that an order by or group by operation is inefficient. Create a composite index that matches the order by columns in sequence. Extra, using temporary. Often caused by group by, distinct, or union operations that cannot effectively use an index. Look for ways to simplify the query or ensure appropriate indexes are in place. High rows count with type, all. A query examining many rows without using indexes, a prime target for optimization. Key, null but possible keys is not empty. MySQL's optimizer chose not to use an available index. This can happen if the table is very small, or the query needs to retrieve a large percentage of the rows, making a full table scan theoretically cheaper. Or if MySQL's statistics are outdated. 6.3. The slow query log. While explain helps analyze a specific query, the slow query log helps you identify which queries are problematic in your running MySQL server. It logs queries that take longer than a certain threshold to execute, enabling and configuring the slow query log. This is typically done in your MySQL configuration file, my.cnf on Linux Mac OS, my.ini on Windows, my.cnf, my.ini. Miscalled, slow query log equals 1 hash enable the slow query log, 1 for on, 0 for off. Slow query log file equals var/log/mysql slow log hash path to the log file. Long query time equals 1.0 hash log queries taking longer than 1 second, can be float, e.g. 0.1. Log query using indexes equals 1 hash log queries that don't use indexes, even if fast. After modifying the configuration file, you'll need to restart your MySQL server for changes to take effect. Sudo systemctl restart miscalled on Linux. Analyzing slow query logs. The slow query log can become very large. Reading it manually is only feasible for a few entries. For automated analysis, tools are invaluable. Miscalldump slow. A command line tool packaged with MySQL that processes slow query logs and summarizes them. It's great for quickly finding the slowest queries and their patterns. Miscalldump slow var/log/mysql slow log. You can use options like st, sort by time, a, don't show numbers in digest, g, select user, only show queries containing select user. Percona Toolkit's PT Query Digest, a more advanced and powerful tool for analyzing various logs, including slow query logs. It provides much more detailed reports and can identify query patterns across large logs. This is a must-have for serious performance analysis. Developer tip. In your development environment, temporarily set long query time to a very low value, e.g., 0.01 or even 0 to catch almost every query and identify potential issues early. Just remember to reset it or disable logging for heavy load testing. 6.4 Profiling queries. While explain shows the plan and the slow query log shows aggregates, a query profiler can show you the time spent in each stage of a single query's execution. This helps pinpoint exactly where the time is being consumed, e.g., parsing, optimizing, sending data, or particular execution steps. Using show profile deprecated but useful for quick checks. Show profile was a simple, in-memory profiler available in older MySQL versions. Still present, but officially deprecated in MySQL 8.0 in favor of performance schema. For quick ad hoc checks in development, it can still be useful. Enable profiling. Set profiling equals 1. Execute your query. Select u.username, p-title from users u-inner join posts p on uid equals p.userid. Show profiles, list recent queries. Show profiles, show detailed profile for a query ID. Show profile for query 1, Replace one with the query ID from Show Profiles. The output will show stages like optimizing, statistics, preparing, executing, sending data, and the time spent in each. Sending data often indicates network latency or the time taken to retrieve and transmit the result set. Tracing query execution with performance schema. Brief intro. Performance schema is a powerful, low-level monitoring and profiling feature in MySQL. It's highly configurable and collects statistics on server events, including query execution. It requires more setup and understanding than Show Profile, but offers much more detailed and persistent insights, suitable for production environments. You typically query views within the performance schema database to get data. For example, you can enable specific consumers to collect statement events, wait events, etc. Select EVENTNAME. TIMERWAIT from performance schema event statement digest order by SUMTIMERWAIT desk can show you the top and most time-consuming normalized queries. Performance schema is a complex topic beyond the scope of a developer-focused book, but it's important to know it's there for deep dive profiling. 6.5 Optimizing SQL Queries, a developer's perspective. Once you've identified slow queries and analyzed their execution plans, it's time for optimization. Rewriting inefficient queries. Avoid select in production. Always specify columns you need. Select pulls unnecessary data, wasting network bandwidth and memory, and potentially preventing covering index usage. Optimize join operations. Ensure join conditions match indexed columns, typically primary foreign keys. Choose the right join type inner, left, right for your actual data needs and expected result set. Filter early. Apply where clauses to the largest tables or the table that reduces the result set the most. Before joining if possible. The optimizer often does this, but clarifying your intent can help. Use union all instead of union when possible. If you don't need duplicate removal, union all is significantly faster as it avoids an expensive sort and deduplicate step. Minimize subqueries or replace with join CTEs. While subqueries can be readable, some, especially correlated subqueries, can be less performant than equivalent joins or common table expressions, CTEs, particularly in older MySQL versions. Consider CTEs for complex logic. Optimizing limit/offset for pagination. For large offset values, limit x offset y can be very slow because MySQL still has to find and discard the first y rows. Solution 1. If order by a unique indexed column. Select id, title from posts where id lasted from previous page, limit page size. This is much more efficient as it uses the index directly. Solution 2. Subquery to find IDs. Select t from posts t. Inner join, select id from posts order by created at DESC limit, 100,000, 10. As subquery ontid equals subquery ID. This fetches only the IDs first, then joins to get the full rows, which can be faster. Indexing revisited, crucial for optimization. Chapter 5 covered this in detail. If explain shows type all or using filesort / using temporary for large tables, your first thought should be, can I add an index here? What to index? Columns in where clauses, join conditions, order by and group by, composite indexes. When filtering and ordering on multiple columns, ensure the index order matches your common query patterns. Basic server configuration for performance, relevant to developers. While largely a DBA's domain, developers should be aware of a few key MySQL server settings that broadly impact performance, as they might be asked to configure their development or staging environments. These are found in my.cnf or my.ini. In node buffer pool size, the most important setting for InnoDB. This is the main memory area where InnoDB caches data and index blocks. Set it to 50 to 80% of your dedicated database server's RAM. If this is too small, MySQL will frequently read from disk, drastically slowing down queries. Query cache size. Deprecated in MySQL 8.0 and removed. In older versions, it cached query results. Sounds good, but it caused significant concurrency bottlenecks and invalidation issues. Do not enable it on MySQL 5.7 Plus or for high concurrency workloads. Max connections. Default is usually 151. If your application often hits too many connections errors, this needs to be increased. However, too many connections can also degrade performance due to increased overhead. Importance of my.cnf, my.ini. These configuration files are where you control almost every aspect of your MySQL server. For production environments, consult with experienced DBAs or use a tool that recommends optimal settings based on your server's resources and workload. 6.6 Monitoring Quick Scan. Beyond logs and explain, real-time monitoring provides continuous insights into your database's health and performance. Show processlist. Shows currently executing queries. id user host db command time, how long the command has been running, state, and info, the actual query, are useful. Look for queries with high time values or states like locked, waiting for table metadata lock. Show full processlist shows the full query text. Show status and show variables. Show status provides a vast array of server status variables, e.g., comSelect for total select statements, handle read and next for full table scans, in nod buffer pool read requests versus in nod buffer pool reads for cache hit ratio. Show variables shows current server configuration variables. You can filter, show status like comSelect%, operating system tools, don't forget basic OS tools. Top or HTOP, Linux, Mac OS, Task Manager, Windows, monitor CPU memory processes. Is MySQL maxing out CPU or RAM? iostat/iotop, Linux. Check disk I/O. Is the database waiting on disk reads writes? Netstat all, network activity. These indicate if the bottleneck is within MySQL itself or the underlying hardware. Overview of monitoring tools. For production, dedicated monitoring solutions are essential. These tools collect metrics, visualize them, and often provide alerts. Prometheus and Grafana, popular open-source combination for collecting and visualizing time series data, requires a MySQL exporter. Percona Monitoring and Management, PMM, a comprehensive open-source platform specifically designed for MySQL, PostgreSQL, and MongoDB monitoring, provides dashboards for query performance, server metrics, and more. Cloud Provider Services. If you're on AWS RDS, Google Cloud SQL, or Azure Database for MySQL, they offer built-in monitoring dashboards and performance insights. Summary of Chapter 6. You've now added a critical skill to your developer toolkit, the ability to diagnose and optimize slow MySQL queries. This often separates competent developers from truly effective ones. You've learned the iterative query optimization process. Identify, analyze, optimize, verify. The indispensable role of explain, how to interpret its output type, rows, extra, to understand query execution plans, identify full table scans, inefficient sorts, using file sort, and temporary table usage, using temporary. How to use the slow query log to find problematic queries on a running server, and miscaldump slow for basic analysis. Basic query profiling with show profile for development, and a conceptual understanding of performance schema. Practical SQL query optimization techniques. Avoiding select, optimizing join-s, using union all, replacing inefficient subqueries, and optimizing pagination. Awareness of key MySQL server configuration settings in nod buffer pool size, max connections that impact performance. Basic monitoring techniques using show processlist and show status, and an overview of professional monitoring tools. With these techniques, you're well equipped to tackle many common performance challenges in your applications. Remember, optimization is continuous. Constantly analyze, test, and refine your queries as your application grows and its data evolves. In the next chapter, we'll shift our focus to data integrity and reliability, transactions and concurrency control, which are fundamental to building robust, multi-user applications. Chapter 7. Transactions and concurrency control. In the previous chapters, we focused on manipulating and optimizing data. Now, we turn our attention to one of the most critical aspects of reliable database operations, transactions and concurrency control. These concepts are fundamental to ensuring data integrity, especially in applications where multiple users or processes might be trying to read or modify data simultaneously. Imagine a banking application. If two people try to transfer money from the same account at the exact same moment, how does the database prevent incorrect balances? What if a power outage occurs in the middle of a complex financial operation? Transactions and concurrency control mechanisms are designed to handle precisely these scenarios, guaranteeing data consistency and reliability. 7.1 What are transactions? A transaction is a single logical unit of work that contains one or more SQL statements. The database management system guarantees that either all the statements within a transaction are successfully executed and recorded, or none of them are. There is no partial completion. The need for reliability and data integrity. Consider a common scenario: transferring money from one bank account to another. This operation involves at least two steps: decrementing the balance in the source account, incrementing the balance in the destination account. If step 1 succeeds, but step 2 fails, e.g., due to a system crash, network error, or invalid account number, the money would be debited from the source account but never credited to the destination. The money would simply vanish, leading to data inconsistency. Transactions prevent this. They ensure that both operations either complete successfully as a whole, or if any part fails, the entire operation is undone, and the database is returned to its state before the transaction began. Atomic, consistent, isolated, durable acid, properties explained. Transactions are characterized by 4 key properties, often referred to by the acronym ACID. Atomicity. All or nothing, a transaction is treated as a single, indivisible unit. It either completes entirely, commits, or has no effect at all, rolls back. If any part of the transaction fails, the entire transaction fails, and the database is restored to its state before the transaction started. This directly addresses the money transfer problem described above. Consistency. A transaction brings the database from one valid state to another valid state. It ensures that all data integrity rules, like primary keys, foreign keys, constraints, and business rules, are maintained. If a transaction attempts to violate these rules, it is aborted, and the database remains in its prior consistent state. Isolation. Concurrency control, the execution of concurrent transactions, produces the same result as if they were executed sequentially, one after another. This means that one transaction's intermediate, uncommitted changes are not visible to other concurrent transactions. This prevents issues like dirty reads, non-repeatable reads, and phantom reads, which we'll explore in detail. Durability. Once a transaction has been committed, its changes are permanent and will survive any subsequent system failures, such as power outages or crashes. The committed data is written to stable storage, and recovery mechanisms ensure it's not lost. These ACID properties are the backbone of reliable RDBMS and explain why databases like MySQL, especially with InnoDB, are so trusted for critical data. 7.2 Commit, rollback, and SAVPONT. Working with transactions involves explicit commands to signify their beginning, processing, and end. Starting a transaction. Start transaction/begin. In MySQL, you typically start a transaction using start transaction or begin. These commands initiate a new transaction scope. Start transaction or begin. Anything you do after start transaction and before commit or rollback is part of that transaction. Saving changes, commit. Commit makes all changes within the current transaction permanent. Once committed, the changes are written to the database and cannot be undone except through a separate restore operation. Start transaction. Perform some DML operations here. Insert into users, username, email, password hash. Values tempuser, temp@example.com, tempfesh. If all goes well, commit. Commit undoing changes, rollback. Rollback undoes all changes made since the beginning of the current transaction. It's like pressing an undo button for data modifications. Start transaction. Insert into posts, userid, title, content, status. Values 999, invalid post. This post will be rolled back. Draft. User ID 999 likely doesn't exist. Something went wrong, e.g., userid 999 violated foreign key constraint, or an application error occurred. Rollback. The insert operation is completely undone. No invalid post will be in the database. Partial rollbacks, SAVPOINT. SAVPOINT allows you to set a named point within a transaction to which you can later roll back. This is useful for complex transactions where you might want to retry a specific part of the operation without discarding the entire transaction. Start transaction. Step 1. Create a new user. Insert into users, username, email, password hash, values, new author, new@example.com, new hash. Let's assume the user gets ID 5. Set it new surid equals lastnsrtid. SAVPOINT user created. Set a save point here. Step 2. Try to create a post for this user. Insert into posts, userid, title, content, status values at new surid. My first post, content, draft. If post creation failed for some reason, roll back only that part. Rollback TO, SAVPOINT user created. Then you could try again or handle the error. If both steps ultimately succeed, commit to roll back to a save point. Roll back to SAVPOINT savepoint name. To release a savepoint, making it unavailable for rollback but keeping changes, release SAVPOINT savepoint name. 7.3 Transaction Isolation Levels. Isolation is about how a transaction's operations are affected by and affect other concurrent transactions. Different isolation levels define the degree to which one transaction's uncommitted changes become visible to others. Higher isolation means more consistency, but potentially lower concurrency. Transactions might wait longer. MySQL's default storage engine, InnoDB, implements the SQL standard isolation levels. Read uncommitted. Dirty reads allowed. A transaction can read data that has been modified by another transaction but not yet committed. If that other transaction then rolls back, the first transaction will have read dirty, non-existent data, leading to inconsistency. Use case: almost never recommended for production. Only in very specific analytical reporting scenarios where data freshness is less important than speed and some inaccuracy is tolerated. Read committed. No dirty reads. A transaction can only read data that has been committed by other transactions. Non-repeatable reads allowed. If a transaction reads the same row multiple times and another committed transaction modifies that row in between, the first transaction might read different values each time. Use case: common default in many other databases, PostgreSQL, SQL Server. Good balance for many web applications. Repeatable read, MySQL default for InnoDB. No dirty reads, no non-repeatable reads. Once a transaction has read a row, it will always see the same version of that row for the duration of the transaction, even if another transaction modifies and commits changes to that row. Phantom reads, usually mitigated by InnoDB. A phantom read occurs when a transaction re-executes a query returning a set of rows and finds that the set of rows has changed. For instance, new rows that matched the queries where clause were inserted by another committed transaction. InnoDB's multi-version concurrency control, MVCC, and next key locking largely prevent phantom reads for select. For update and select, lock in share mode queries, and for consistent reads, select without explicit locking. Use case: good for long-running reports or batch processes where data consistency for all reads within the transaction is paramount. SCRIALIZABLE. Highest isolation, lowest concurrency. This level guarantees full isolation, meaning concurrent transactions behave as if they were executed sequentially. It prevents dirty reads, non-repeatable reads, and phantom reads. It typically achieves this by placing read locks on all data read by a transaction, which can significantly reduce concurrency. Use case: ideal for scenarios requiring absolute data consistency, such as critical financial reconciliations or auditing, where performance is less critical than strict correctness. You can set the isolation level for the entire session or for a single transaction. Set for the current session. Set session transaction isolation level read committed. Set for the next transaction only. Set transaction isolation level, SCRIALIZABLE. Start transaction. Transaction statements. Commit. Choosing the appropriate isolation level. For most typical web applications using MySQL/InnoDB, repeatable read, the default, is a good starting point and often sufficient. If you encounter specific concurrency problems, like phantom reads, you might temporarily use scalable to confirm the issue, and then look for more granular locking or application-level solutions. For high-throughput applications, where some eventual consistency is acceptable, Red Committed can offer better concurrency. 7.4 Concurrency Control, locks, to achieve isolation and prevent conflicts when multiple transactions access the same data. Databases employ various locking mechanisms. MySQL in NoDB uses sophisticated row-level locking. Shared read locks, slocks, acquired when a transaction needs to read data. Multiple transactions can hold shared locks on the same data simultaneously. A shared lock prevents an exclusive lock from being placed on the data. Exclusive write locks, xlocks, acquired when a transaction needs to modify, insert, update, delete data. Only one transaction can hold an exclusive lock on a piece of data at a time. An exclusive lock prevents any other shared or exclusive locks from being placed on the same data. Row-level Vs. Table-level locking. Row-level locking in NoDB locks only the specific rows or even just index records pointing to rows that are being accessed. This allows high concurrency, as different transactions can modify different rows in the same table simultaneously. This is the primary mode for in NoDB. Table-level locking, MyISAM, locks the entire table even for a single row modification. This leads to much lower concurrency, as only one write operation can occur on a table at a time. This is why in NoDB is preferred for almost all web applications. Implicit versus explicit locking. Implicit locking. Most locking in a NoDB is implicit. When you execute an update or delete statement within a transaction, in NoDB automatically acquires the necessary exclusive row locks. When you select under repeatable read, the default, in NoDB uses consistent reads, MVCC, which typically don't acquire explicit shared locks by default, reading a snapshot of the data. Explicit locking, you can manually request shared or exclusive locks using select, for share, shared lock, formerly lock and share mode, or select, for update, exclusive lock. Select, for update, locks the fetched rows with an exclusive lock. Other transactions cannot read or modify these rows until this transaction commits or rolls back. Useful when you need to read a row and then immediately update it within the same transaction, preventing a lost update. Select, for share, locks the fetched rows with a shared lock. Other transactions can read but not modify these rows until this transaction commits or rolls back. Example, select, for update. Start transaction. Select balance from accounts where id equals 123 for update. Assume balance is 100. Update account set balance equals balance 50, where id equals 123. Now balance is 50. Commit. If another transaction tried to read or modify accounts, id equals 123 immediately after the select. For update, it would wait until the first transaction commits or rolls back. 7.5 Common concurrency problems. Understanding transactions and locking helps prevent common problems that arise when multiple operations access the same data concurrently. Race conditions. Problem. When multiple threads processes try to access and modify a shared resource, like a database record, at the same time, and the final outcome depends on the non-deterministic order in which they execute. Example. Two users try to reserve the last available item in an inventory system. Both read that stock equals 1. Both then proceed to stock 1, resulting in stock equals 0, but both users think they reserved an item. Solution. Use transactions with appropriate locking, select, for update, to ensure that the read and subsequent update are atomic and isolated. Deadlocks. Problem. A deadlock occurs when two or more transactions are waiting indefinitely for each other to release locks that they need. Scenario. Transaction A locks row 1, then tries to lock row 2. Transaction B locks row 2, then tries to lock row 1. Both are now stuck waiting for the other to release the lock they need. Detection and resolution. In NoDB automatically detects deadlocks. When a deadlock is detected, it typically rolls back one of the transactions, the deadlock victim, to break the cycle and allow the other transaction to proceed. The rolled back transaction will receive an error and needs to be retried by the application. Prevention: acquire locks in a consistent order. Always try to lock resources, rows, in the same order across all your transactions. Keep transactions short. The less time a transaction holds locks, the less chance of a deadlock. Index columns used for locking ensures row-level locks are used efficiently. Use select for update for update operations. How to handle errors and rollbacks gracefully in application code. Given that deadlocks can occur and are often normal in highly concurrent systems, your application code must be prepared to handle them. When a database operation fails due to a deadlock, MySQL, or your database driver ORM, will typically throw an error, e.g., error code 1213 in MySQL. Your application should catch this specific error and then retry the entire transaction from the beginning. Implementing a few retry attempts with a small exponential backoff can resolve many transient deadlock issues. 7.6 Example: implementing a safe money transfer. Let's illustrate the power of transactions with a simple, conceptual money transfer example. Imagine an accounts table. Create table accounts. int primary key. Name varchar 255. Balance decimal 10.2. Engine equals in NoDB. Insert into accounts name balance values. 1 Alice 1000.00. 2 Bob 500.00. Now let's transfer $200 from Alice ID 1 to Bob ID 2. Start transaction. 1 Check Alice's balance and lock her row. Select balance from accounts where id equals 1 for update. Application logic. If balance 200, rollback. 2 Debit Alice's account. Update account set balance equals balance 200 where id equals 1. 3 Credit Bob's account and lock his row. Select balance from accounts where id equals 2 for update. If separate for safety, update account set balance equals balance plus 200 where id equals 2. If all operations succeed, commit the transaction. Commit: if any operation fails, e.g., Alice has insufficient funds or a network error. Rollback: why this is safe. Atomicity: if the update to Bob's account fails, the entire transaction is rolled back and Alice's account remains at $1,000. No money is lost or created unexpectedly. Isolation: if another transaction tries to read or modify Alice's or Bob's account balance while this transfer is in progress, the FOR update clause ensures that those other transactions either wait or see a consistent prior state, preventing dirty reads or lost updates. Consistency: the sum of balances, 1,000 plus 500 equals 1,500, will remain consistent, 800 plus 700 equals 1,500, before and after the transaction. Durability: once commit is executed, the new balances are permanently recorded, even if the server crashes immediately after. Summary of Chapter 7. Transactions and concurrency are not abstract database concepts. They are vital for building robust, reliable, and scalable applications. You now have a solid understanding of ACID properties, the 4 pillars atomicity, consistency, isolation, durability that define a reliable transaction. Transaction commands: how to use start transaction begin, commit, rollback, and savepOINT to control your units of work. Isolation levels: the different degrees of visibility between concurrent transactions, read uncommitted, read committed, repeatable read, SCRIALIZABLE, and their associated concurrency issues, dirty reads, non-repeatable reads, phantom reads. Concurrency control with locks: how InnoDB uses shared and exclusive row-level locks to manage simultaneous access. Select for update and select for share: how to explicitly acquire locks for specific use cases. Common concurrency problems: understanding race conditions and deadlocks and strategies for prevention and graceful handling, like retries in application code. Practical application, illustrated with a safe money transfer example. Equipped with this knowledge, you can confidently design and implement application logic that operates securely and reliably on your MySQL database, even under heavy load. In the next chapter, we'll delve into stored routines, triggers, and views, powerful server-side features that can encapsulate logic, enforce business rules, and simplify complex queries. Chapter 8. stored routines, triggers, and views. So far, we've focused on SQL commands that are executed directly and immediately by your application. However, MySQL offers powerful features that allow you to store SQL code directly within the database server. These features, stored procedures, stored functions, and triggers, let you encapsulate logic, centralize business rules, and sometimes improve performance. Additionally, views provide a way to simplify complex queries and enhance security. As a developer, these server-side objects can be incredibly useful for tasks that require consistency, security, or performance benefits not easily achieved with plain client-side SQL queries. 8.1 Stored Procedures. A stored procedure is a named set of SQL statements that are stored in the database. Once created, you can call or execute the procedure by its name, and it will run the encapsulated SQL logic. Why use stored procedures? Encapsulation and modularity. They act like functions in programming languages, allowing you to bundle a complex series of SQL operations into a single, reusable unit. This makes your application code cleaner and reduces repetitive SQL. Performance. Reduced network traffic. Instead of sending multiple SQL statements over the network, your application sends just one command to execute the procedure. Pre-compiled cached execution plans. MySQL compiles stored procedures once and caches their execution plans. Subsequent calls can often use the cached plan, saving compilation time. Security. You can grant users permission to execute a stored procedure without granting them direct access to the underlying tables. This can be a powerful security mechanism for sensitive operations. Centralized logic. Business rules and complex data manipulations can be centralized in the database. This ensures consistency across different applications that use the same database. Creating a simple stored procedure. When creating stored procedures and functions and triggers, you often encounter the delimiter command. This is because a stored procedure can contain multiple SQL statements, each ending with a semicolon. If you're typing these directly into the MySQL command line client or some GUI tools, the client would interpret the first semicolon as the end of your create procedure statement, leading to syntax errors. The delimiter command temporarily changes the statement terminator from to something else, e.g. After you've defined your procedure, you change it back to. Let's create a procedure to register a new user in our blog platform database. Delimiter. Create procedure register user. In username varchar 50. In pmail varchar 100. In password hash varchar 255. Begin. Insert into users, username, email, password hash. Values, username, pmail, password hash. End. Delimiter, explanation for audio, delimiter $. This line tells the MySQL client to now use as the end of statement delimiter instead of the default semicolon. Create procedure register user. This starts the definition of a new stored procedure named register user. In username varchar 50. These lines define the input parameters for the procedure. It indicates that these parameters are passed into the procedure. P is a common prefix for procedure parameters to avoid name clashes with column names. Begin, end. These keywords define the body of the procedure, containing the SQL statements. Insert into users. This is the actual SQL statement that adds a new row to the user's table using the provided parameter values. $. This marks the end of the create procedure statement as defined by our temporary delimiter. Delimiter, this restores the delimiter back to the standard semicolon. Input, output, and in-out parameters. In, the parameter passes a value into the procedure. It cannot be modified by the procedure. Used above. Out, the parameter passes a value out of the procedure back to the caller. The procedure can modify this parameter, but the caller's initial value is not passed in. INOUT. The parameter passes a value both into and out of the procedure. The procedure can read and modify its value. Example without parameter, getting the new user ID. Delimiter. Create procedure, register user and getted. In username varchar 50. In pmail varchar 100. In password hash varchar 255. Out pnuserid int. Begin. Insert into users, username, email, password hash. Values, username, pmail, password hash. Set pnuserid equals lastdinsrtid. Get the last inserted auto-increment ID. And delimiter, control flow, brief overview. Stored procedures can contain advanced procedural logic, making them more powerful than simple SQL statements. If, then, ELSEIF, then, else, and if for conditional execution, case, when, then, else, end case, another way to handle multiple conditions. Loop and loop. For creating basic loops, with leave to exit, iterate to continue. While condition do, end while, loops based on a condition. Repeat, until condition end repeat, loops until a condition is met. For audiobook compatibility, we won't show full code blocks for these, but understand they allow you to create complex logic trees within your database. For instance, you could have a procedure that checks user permissions before performing an insert, or loops through a set of data to perform an operation on each row. Variables. You can declare and use local variables within a stored procedure. Declare viewserCount int default 0, select count, into viewserCount from users. Here, viewserCount is a local variable. Calling and dropping procedures. To execute a stored procedure, call register user, SusanReader, susan@example.com, susan#111. To call a procedure with an out parameter, you need a session variable. Call register user and get ID DanielAdmin, daniel@example.com, Daniel#222 at userItout, select at userItout. To see the value returned in the out parameter. To remove a stored procedure, drop procedure if exisds register user. 8.2 Stored functions. A stored function is similar to a stored procedure, but with key differences. The most important difference is that a stored function always returns a single scalar value and can be used directly within SQL expressions, e.g., in a select list, where clause or insert statement. Differences from stored procedures. Return value. Functions must have a returns clause and return a value using return. Procedures do not return values, but can use out parameters. Usage in SQL. Functions can be used directly in SQL queries where an expression is expected, e.g., select my function, from table. Procedures are called using the call statement and treated as statements themselves. Data modification. Generally, stored functions are not allowed to perform data modifications, i.e., insert, update, delete, if they are deterministic or read SQL data. MySQL relaxes this rule somewhat, but it's a good practice to keep functions as side effect free as possible for clarity and predictability. Creating and calling a stored function. Let's create a function to get a user's full name. If we had first and last names in the user table, otherwise, just return username for demonstration. Delimiter. Create function, get user display name pnuserid int. Returns varchar 100. Deterministic indicates that for the same input, it will always return the same output. Begin. Declare user display name varchar 100. Select username into user display name from users where id equals pnuserid. Return user display name. End. Delimiter explanation for audio. Create function get user display name. Defines a function. Returns varchar 100. Specifies the data type of the value the function will return. Deterministic, an important keyword. It tells MySQL that the function will always produce the same result for the same input parameters. This allows MySQL to optimize better, e.g., cache results. If the function queries data that might change, you might need read SQL data or modifies SQL data, but deterministic is stricter. Return user display name. The return statement is used to send the computed value back, calling a stored function. Select get user display name 1, returns John Doe. Select title, get user display name, userid as author name from posts. Explanation for audio. In the second query, the function get user display name is called for each row in the posts table, using the userid from that row as an input, and the result is returned as a column named author name. Limitations of stored functions. Cannot return result sets, multiple rows, multiple columns. For that, you need procedures. Should ideally not perform DML operations directly, though MySQL allows it with specific characteristics. This is a common point of contention. Many consider DML in functions an anti-pattern. 8.3 Triggers. A trigger is a special type of stored procedure that automatically executes, or fires, when a specific database event occurs on a specified table. These events are insert, update, or delete operations. What are triggers and their use cases? Triggers are powerful for enforcing complex business rules and automating tasks at the database level. Auditing. Recording changes to sensitive data, e.g., logging who changed what, when, to which value. Enforcing business rules. Ensuring data consistency that cannot be enforced by simple constraints, e.g., ensuring a product's price is always greater than its cost. Data synchronization. Automatically updating other tables when data changes in one table, e.g., updating a last modify date in a parent record when a child record is updated. Calculated columns. Maintaining aggregate values, e.g., total orders for a customer, without explicitly querying every time. Before versus after triggers. Triggers can fire before or after the event. Before trigger executes before the SQL statement affects the table. Useful for data validation or manipulation before the change is written, e.g., formatting data, preventing an insert if a condition isn't met. Can modify the new values for insert or update operations. After trigger executes after the SQL statement has affected the table. Useful for logging changes, updating related tables, or performing actions based on the final state of the row. Cannot modify the new values from the current statement, the change has already happened. Insert, update, delete events. Triggers are assigned to specific events. For insert, fires when a new row is inserted. For update, fires when an existing row is updated. For delete, fires when an existing row is deleted. Old and new row references. Inside a trigger, you can refer to the row being affected using old and new pseudorecords. New refers to the new row for before insert, after insert, or the new values of an updated row for before update, after update. Old refers to the old row for before delete, after delete, or the old values of an updated row for before update, after update. You access columns like new.column name or old.column name. Creating triggers. Let's create a trigger to automatically maintain update timestamps. Although our table DDL already handles this implicitly for timestamp columns. This shows how you do it manually or for DAT/TIME columns. Delimiter. Create trigger before post update. Before update on posts for each row. Begin. Set any wupdate equals now. Set the update dat to the current timestamp. End. Delimiter. Explanation for audio. Create trigger before post update. Defines a trigger named before post update. Before update on posts, specifies that this trigger fires before any update operation on the posts table. For each row, indicates that the trigger logic will execute for every row affected by the update statement. Set any wupdate equals now. Inside the trigger, any wupdate refers to the update column of the row about to be updated. This line sets its value to the current timestamp, now, before the update is committed. Example 2. Auditing deleted comments. Imagine we have an audits table. Create table audits. id int autoincrment primary key, table name varchar 255, recorded int, action type varchar 50, old dated syntax, changed at timestamp default currentTMSTMP. Delimiter. Create trigger after comment delete. After delete on comments for each row. Begin. Insert into audits. Table name, recorded, action type, old dated syn. Values, comments, olded, delete, JSON object. Content, old.content, userid, old.userid, created at, old created at. End. Delimiter, explanation for audio. This trigger fires after delete on the comments table. For each deleted row, it inserts a record into the audits table, capturing the table name, the ID of the deleted comment, olded, the action type, and a JSON representation of the old row's content. Dropping triggers. Drop trigger if exists before post update. Pros and cons of using triggers. Pros, automated enforcement. Ensures business rules are applied consistently regardless of how data is modified, whether by application, manual query, or other procedures. Data integrity can prevent invalid data states that application code might miss. Reduced application code offloads some logic to the database server. Cons, hidden logic. Logic inside triggers is not immediately visible when looking at application code, potentially making debugging and understanding system behavior harder. Performance overhead. Triggers add overhead to DML operations. Poorly written triggers can significantly slow down your writes. Complexity can make database schema more complex and harder to maintain. Debugging challenges. Debugging trigger logic can be more difficult than debugging application code. Developer recommendation. Use triggers judiciously. Prefer application-level logic for most business rules, especially if they are complex or change frequently. Use triggers for truly atomic, data integrity-critical rules that belong inherently to the database schema, like auditing sensitive changes or maintaining materialized views. 8.4 Views. A view is a virtual table based on the result set of a select query. It contains no data itself. Instead, it's a window into the data of one or more underlying base tables. What are views and their purpose? Views provide several benefits. Simplification. Complex queries with many joins, aggregations, or subqueries can be encapsulated within a view. Developers then just query the view as if it were a simple table. Security. You can grant users access to a specific view that exposes only a subset of columns or rows from a sensitive table, rather than granting direct access to the table itself. Abstraction. If your underlying table schema changes, you can modify the view definition without affecting applications that query the view, as long as the view's output columns remain consistent. Reporting. Ideal for predefining common reports or datasets. Creating a simple view. Let's create a view that gives us published posts with their author's username. Create view published posts with authors as. Select p as posted, p-title as post title, p.content as post content, p-published at, u.username as author username, u-email as author mail. From, posts as p, inner join, users as u, onp.userid equals uid. Where, p-status equals published. Explanation for audio. Create view published posts with authors as defines a new view named published posts with authors. Select from where. This is the standard select query whose result set defines the view. Now you can query this view as if it were a table. Select post title, author username. From published posts with authors. Where author username equals John Doe. Explanation for audio. This query now looks much simpler, as it queries the published posts with authors view directly, without needing to know about the underlying posts and users tables, the join condition, or the status filter. Updatable views and their limitations. Some views are updatable, meaning you can perform insert, update, or delete operations directly on them, and MySQL will attempt to translate those operations back to the underlying base tables. However, not all views are updatable. A view is updatable if and only if the FROM clause refers to only one table, and nothing prevents the view from uniquely mapping rows of the view to rows of the base table. Typically, views that are not updatable include those that use aggregate functions, sum, count, avg, etc., contain distinct, group by, having, union, or union all, include subqueries in the select list, are derived from join operations, like our published posts with authors view. For complex views, it's safer and clearer to have your application perform DML operations directly on the base tables. For simple, single-table views, e.g., create view active users as select id, username, email from users where status equals active. They can be updatable. Dropping views. Drop view if exists published posts with authors. Practical uses of views in application development. Simplifying complex reports. As shown, a view can abstract away a complex report query into an easily consumable table. Security layer. Create views that expose only non-sensitive columns or rows based on user roles. For instance, a user public profile view might exclude password hash and email columns. Schema evolution. If you need to refactor your database by splitting a table, you can create a view with the old table's name that joins the new tables, allowing applications to continue working without modification. Summary of Chapter 8. This chapter introduced you to the powerful world of database-side logic and abstraction, allowing for more robust, secure, and potentially performant applications. You've learned about stored procedures. Encapsulating multi-step SQL logic using input and output parameters and benefiting from reduced network traffic and precompiled execution plans. Stored functions. Similar to procedures, but designed to compute and return a single scalar value, usable directly within SQL expressions. Triggers. Automating actions in response to insert, update, or delete events with before and after timings, and access to old and new row values for auditing and enforcing complex business rules. Views. Creating virtual tables for simplifying queries, abstracting schema complexity, and enhancing security by exposing only necessary data. While these features offer significant advantages, remember their trade-offs, especially regarding hidden logic and potential performance implications of triggers. Use them strategically where they provide clear benefits for data integrity, performance, or security, distinguishing between logic that belongs in the database versus the application tier. In the next chapter, we'll turn our attention to the critical topic of securing your database, covering user management, privilege control, and preventing common vulnerabilities like SQL injection. Chapter 9. Securing your database. Congratulations! You've mastered querying, optimizing, and ensuring transactional integrity in your MySQL database. Now, let's talk about perhaps the most critical aspect of any database system: security. In a world where data breaches are daily headlines, protecting your database is not an option. It's a fundamental responsibility. For a developer, understanding database security goes beyond just preventing SQL injection. It involves knowing how to manage user access, control permissions granularly, secure communication, and implement best practices that safeguard your application's most valuable asset: its data. This chapter will equip you with the knowledge to build more secure MySQL-backed applications. 9.1. The importance of database security. Why is database security so paramount? Because your database is typically the central repository for sensitive, valuable, and often irreplaceable information. This includes personal identifiable information, PII, usernames, emails, phone numbers, addresses, financial details, business-critical data, sales records, inventory, intellectual property, confidential documents, authentication credentials, user passwords hopefully hashed as we discussed, API keys. A security breach can lead to financial loss, fines, litigation, lost revenue due to downtime, reputational damage, loss of customer trust, negative publicity, legal consequences, violations of data protection regulations, e.g., GDPR, HIPAA, CCPA, operational disruption, data loss, corruption, system outages. Common threats developers should be aware of include SQL injection, exploiting vulnerabilities in application code to execute malicious SQL commands, unauthorized access, gaining access to the database by guessing passwords, exploiting weak configurations, or using stolen credentials, data exfiltration, stealing sensitive data, privilege escalation, a low-privileged user gaining higher, unauthorized permissions, denial of service, DoS, overwhelming the database to make it unavailable. The principle of defense in depth is key, implementing multiple layers of security so that if one layer fails, others are still in place to protect your data. 9.2. User management. The first line of defense is controlling who can access your database. MySQL allows you to create users and specify which hosts they can connect from. Creating users, create user. When you install MySQL, there's typically a root user who has all privileges. For security, you should avoid using root for your applications. Instead, create specific users with only the permissions they need. Create user abuser at localhost, identified by your strong password here, or for remote access from a specific IP. Create user adminuser at 192.168.1.100, identified by another strong password, or for remote access from any host, less secure, use with caution. Create user any user at %, identified by yet another password. Use a plugin like Catching Should a Password for better security, MySQL 8.0 default. Create user secure user at localhost, identified with Catching Should a Password, by even stronger password. Explanation for audio. The create user statement specifies a username and the host from which they can connect. Localhost means connections only from the same machine where MySQL is running. A specific IP address limits connections to that IP. The percent wildcard means connections from any host, which should be used with extreme caution and combined with strong network firewalls. The identified BY clause sets the password. For MySQL 8.0 and newer, catching should a password is the default and most secure authentication plugin, ensuring stronger password hashing. Renaming and dropping users. To rename a user, rename user old-user at localhost to new-user at localhost. To remove a user, which also revokes all their granted privileges. Drop user abuser at localhost. Password management and policies. Strong passwords always enforce complex, long passwords for database users. Password rotation, implement policies for regular password changes. No default passwords. Change all default passwords immediately after installation. Avoid hard-coding passwords. Never embed passwords directly in your application code. Use environment variables, configuration files, or secure secret management services. 9.3. Granting and revoking privileges. Creating users is just the first step. You then need to define what those users are allowed to do. This is managed through privileges or permissions. Grant statement. The grant statement assigns privileges to users. Grant privilege type on database name table name to user at host. Common privilege types. Select, read data from tables. Insert, add new rows to tables. Update, modify existing rows. Delete, remove rows. Create new tables, databases, or indexes. Alter, change table structure. Drop, delete tables or databases, all privileges. Grants all available privileges, use with extreme caution. Levels of privilege. You can grant privileges at different granularities. Global level applies to all databases and all tables on the server. Only grant this for administrative users like root. Grant all privileges on. To debosser at localhost, database level, database name, applies to all tables within a specific database. This is a common level for application users. Grant select, insert, update, delete on BlogPlatform. To abuser at localhost. Explanation for audio. This grants the abuser the common CRUD, create, read, update, delete permissions on all tables within the BlogPlatform database. Table level database name table name applies only to a specific table within a specific database. Grant select, insert on blogplatform.users to registration worker at localhost. Explanation for audio. This registration worker user can only select from and insert into the user's table within BlogPlatform. They cannot update or delete users and cannot access other tables. Column level, database name table name, column name. The most granular applies only to specific columns within a table. This is less common for DML but useful for update or select privileges. Grant update, password hash on blogplatform.users to password-rested service at localhost. Explanation for audio. This password-rested service user can only update the password hash column on the users table, not other columns like username or email, and cannot access other tables. Revoke statement. The revoke statement removes privileges previously granted to a user. Revoke insert on BlogPlatform posts from abuser at localhost. Explanation for audio. This command removes the insert privilege on the posts table from abuser. The user would still retain any other privileges they had. The principle of least privilege. This is a fundamental security principle. Always grant users only the minimum set of privileges necessary to perform their required tasks, and no more. Your web application user should typically only have select, insert, update, delete on the tables it needs to interact with. Avoid granting all privileges or drop permission to application users. Separate users for different application components if possible, e.g., one user for reading, another for writing, a third for administrative tasks. 9.4. Preventing SQL injection. SQL injection remains one of the most prevalent and dangerous web application vulnerabilities. It occurs when an attacker can trick your application into executing malicious SQL commands by injecting SQL code into input fields. Understanding the vulnerability. Imagine your application builds a query like this. Select from users where username equals user input. If a user enters John Doe as user input, the query becomes. Select from users where username equals John Doe. Harmless. But if an attacker enters admin or 1 equals 1 as user input, the query becomes. Select from users where username equals admin or 1 equals 1. The 1 equals 1 is always true, so the where clause becomes true for all rows, potentially returning all user data, including admin passwords. Even worse, an attacker could enter admin, drop table users, is a comment in SQL, ignoring the rest of the original query. Select from users where username equals admin, drop table users. This would execute the drop table users command, deleting your entire user database. Prepared statements, primary defense. The primary and most effective defense against SQL injection is to use prepared statements, also known as parameterized queries. A prepared statement works by first sending the SQL query structure, the template, to the database separately from the actual user data. The database compiles this template and notes where the parameters are, often using placeholders like or named parameters. When you then provide the data values, the database knows they are data and treats them as such, never interpreting them as executable SQL code. Conceptual example, language agnostic. Prepare the statement once. MySQL prepare. Select from users where username equals and password. The database sees username equals placeholder and password equals placeholder. Execute the statement multiple times with different data. MySQL bind param. SS. User input, password input. Bind user-provided strings user input and password input to the placeholders. MySQL execute, explanation for audio. The crucial point is that the database already understands the structure of the query before it receives any user-provided data. It creates a clear separation between the SQL code and the values being inserted into that code. This prevents an attacker's input, like drop table users, from being interpreted as a command. Instead, it's treated just as a literal string value for the username or password. Actionable advice. Every programming language and its database connector. Python's MySQL connector, Node.js, MySQL2, PHP's PDO or MySQLi, Java's JDBC, C#sado.net provides support for prepared statements. Always use them for any database query that involves user-provided input. Input validation and sanitization, secondary defenses. While prepared statements are the main defense, client-side and server-side input validation and sanitization add extra layers of security. Validation, ensuring that user input conforms to expected formats, e.g., an email address actually looks like an email, a number is truly numeric. A username contains only alphanumeric characters. This can prevent malformed input from even reaching the database. Sanitization, cleaning or encoding input to remove or neutralize potentially harmful characters. While prepared statements handle SQL injection, sanitization is still important for preventing other vulnerabilities like cross-site scripting, XSS. Escaping special characters, last resort/legacy. This technique involves escaping or quoting characters that have special meaning in SQL, like single quotes, backslashes, etc. Functions like MySQL escape string. In older PHP MySQL APIs perform this. However, this is not a primary defense against SQL injection and should be avoided in favor of prepared statements. It's difficult to implement correctly and consistently across all contexts, and often misses edge cases or new injection techniques. Consider it a legacy approach for systems that cannot adopt prepared statements. 9.5 Network security considerations. Even with strong user management and injection protection, you need to ensure your database server is not directly exposed where it shouldn't be. Firewall rules. By default, MySQL listens on port 3306. Your server's firewall, e.g., UFWA on Linux, Windows Firewall, should only allow connections to port 3306 from trusted IP addresses or application servers. Never expose port 3306 directly to the public internet unless absolutely necessary. And then, only with extreme caution and other security measures like VPNs or strong SSL TLS. Your application server should connect, not end-user devices. Binding to specific IP addresses. In your MySQL configuration file, my.cnf, the bind address parameter specifies which network interface MySQL should listen on. Bind address equals 127.0.0.1 or localhost means MySQL will only accept connections from the local machine. This is ideal for development and if your application is on the same server. If your application server is separate, bind address should be set to the internal IP address of the database server, not a public one. SSL TLS encryption for client-server communication. Just as you use HTTPS for web traffic, MySQL connections should be encrypted, especially over untrusted networks. SSL TLS, Secure Sockets Layer Transport Layer Security, encrypts data transmitted between your application and the MySQL server, preventing eavesdropping. MySQL clients and connectors support SSL TLS configuration. You'll typically need to generate or obtain SSL certificates for your server and configure your application client to use them. 9.6 Data Encryption. Data encryption protects information from unauthorized access, both when it's being transmitted and when it's stored. Encryption at rest, data on disk, file system encryption, encrypting the entire disk or a portion of the file system where MySQL data files, FRM, IBD, are stored. This is often handled by the operating system, e.g., Linux's LUKS, Windows BitLocker. Transparent Data Encryption, TDE, available in MySQL Enterprise Edition. TDE automatically encrypts data files, table spaces, at the storage level. Data is encrypted when written to disk and decrypted when read, transparently to the application. Application-level encryption. For highly sensitive data, like credit card numbers or highly personal PII, you might encrypt individual data fields before storing them in the database. Your application would then decrypt them after retrieval. This puts the encryption key management and decryption logic onto the application. Encryption in transit, data over network. This is covered by SSL TLS, Secure Sockets Layer Transport Layer Security for client-server connections, as discussed in the Network Security section. Hashing passwords, crucial and distinct from encryption. Never store plaintext passwords in your database. Always store hashes of passwords. Hashing is a one-way function. You cannot get the original password back from its hash. When a user logs in, hash their provided password and compare it to the stored hash. Use strong, modern hashing algorithms like bcrypt, script, or Argon2, applied at the application layer, or MySQL's built-in SHA-2, if performing hashing within the database for less sensitive passwords. The SHA-2 password authentication plugin also uses SHA-256 for internal password storage. 9.7 Logging and auditing. Security isn't just about preventing attacks. It's also about detecting them and understanding what happened. MySQL logs. MySQL generates various logs that can be invaluable for security. Error log. Records significant events like server startup shutdown and critical errors. General query log. Records every single query received by the MySQL server. Use with extreme caution. It's highly verbose and can significantly impact performance, making it unsuitable for production unless for very short-term debugging. Slow query log. As discussed in Chapter 6, records queries exceeding a time threshold. Not directly a security log, but can indicate performance issues that could be related to malicious activity. Binary log, binlog, primarily for replication and point-in-time recovery. It records all data-modifying statements, which can be useful for forensic analysis after an incident. Audit log, MySQL Enterprise Edition. For compliance and highly regulated environments, MySQL Enterprise Edition offers an audit log plugin. This logs specific database activities, e.g., user logins, DDL statements, queries on sensitive tables, in a structured and configurable way, providing a detailed trail for security and compliance audits. Importance of monitoring access and changes. Regularly review logs for suspicious activity, e.g., failed login attempts, unexpected DDL commands, access from unusual IP addresses, implement monitoring and alerting systems that notify you of potential security incidents. Summary of Chapter 9. Database security is a continuous process that requires vigilance and adherence to best practices. As a developer, you play a pivotal role in implementing these safeguards. You've now learned the critical importance of database security and common threats, how to effectively manage users, create user, drop user, and enforce strong password policies, the power and precision of privilege management, grant, revoke at global, database, table, and column levels, always adhering to the principle of least privilege, the absolute necessity of prepared statements, parameterized queries, as your primary defense against SQL injection. Key network security measures, including firewall configuration, IP binding, and the essential use of SSL/TLS for encrypted communication. Concepts of data encryption at rest and in transit, and the non-negotiable practice of hashing passwords. The role of various MySQL logs and the importance of monitoring for potential security breaches. By applying these security principles and practices throughout your development lifecycle, you'll be building applications that are not only functional and performant, but also resilient against a wide range of cyber threats, protecting both your data and your users. Next, we'll shift gears from database-side concerns to integrating MySQL with your applications, exploring how your code connects, executes queries, and works with the database. Chapter 10. Integrating MySQL with your applications. You've built a robust database, optimized its performance, and secured its data. Now, it's time to bridge the gap between your application code and your MySQL server. This chapter is all about integrating MySQL with your applications, exploring how your code connects to the database, executes queries, handles transactions, and leverages various tools to streamline development. Whether you're building a web application, a desktop tool, or a backend service, the principles of database interaction remain largely consistent across programming languages and frameworks. We'll focus on the conceptual aspects of this integration, illustrating how you take the SQL you've learned and put it into action within your chosen programming environment. 10.1 Connection Strategies. Before your application can interact with MySQL, it needs to establish a connection. This is typically the first step in any database-driven application, establishing a database connection. At a high level, connecting to MySQL from your application involves loading a database driver connector. Your programming language needs a specific library that understands how to communicate with MySQL. For Python, this might be MySQL connector Python. For Node.js, MySQL 2. For Java, the JDBC driver, and so on. These drivers provide the API for database interaction. Providing connection details, you need to tell the driver where your MySQL server is and how to authenticate. This usually comes in the form of a connection string or a set of parameters. Common parameters include host, the IP address or hostname of your MySQL server, e.g. localhost 127.0.0.1, your .db.server.com. Port. The port number MySQL is listening on default is 3306. User, the username to connect with, e.g. a user from Chapter 9. Password, the password for that user. Database schema, the specific database you want to connect to, e.g. blog platform. Example conceptual connection, not language-specific code. Imagine your application has a configuration file where you store these details. Your code would then call a connect function provided by your database driver, passing in these parameters. For instance, connect host equals localhost, port equals 3306, user equals a user, password equals secure password, database equals blog platform. Security reminder. As discussed in Chapter 9, never embed sensitive connection details like passwords directly in your application source code. Use environment variables, secure configuration files, or secret management services provided by your deployment platform, e.g., AWS Secrets Manager, HashiCorp Vault. Connection pooling, what it is and why it's important. Establishing a database connection is not a free operation. It involves network handshakes, authentication, and resource allocation on both the client and server sides. For applications that handle many concurrent user requests, like web applications, creating a new connection for every request can introduce significant overhead and quickly exhaust server resources. Connection pooling is a technique where a pool, a collection of reusable database connections, is maintained. Instead of creating a new connection for each request, when your application needs a connection, it requests one from the pool. If an idle connection is available in the pool, it's immediately given to the application. If no connections are available, the application might wait until one is released or a new one is created, up to a configured maximum. When the application is done with the connection, it returns it to the pool, making it available for other requests. Benefits of connection pooling. Performance. Reduces connection overhead and latency, making your application faster and more responsive. Resource management. Prevents the database server from being overwhelmed by too many simultaneous connections. Scalability. Allows your application to handle a higher volume of concurrent requests more efficiently. Most modern application frameworks and database drivers, e.g., in Java, Python, Node.js, provide built-in connection pooling functionality or integrate with popular pooling libraries. Handling connection errors. Database connections can fail for various reasons: incorrect credentials, server downtime, network issues, or too many concurrent connections. Your application must gracefully handle these errors. Common strategies include retries, attempting to reconnect a few times with a short delay; logging, recording the error details for debugging and monitoring; user feedback, providing a user-friendly message instead of a generic error page; circuit breakers, temporarily stopping database interactions if too many consecutive errors occur to prevent cascading failures. 10.2. Executing queries from application code. Once a connection is established, your application can send SQL queries to the MySQL server. This involves preparing the query, executing it, and processing the results. Select queries and fetching results. For select queries, your application will prepare the query. Often, this means constructing the SQL string with placeholders for parameters. Execute the query. The driver sends the prepared query and its parameters to the database. Fetch results. The database returns a result set, which your application then processes. Single row. Fetch-on, or equivalent to retrieve one record, e.g., a user by their ID. Multiple rows. Fetch-all, or iterating over the result set to retrieve all matching records, e.g., all blog posts. Pagination. Fetching results in chunks using limit and offset in your SQL, as covered in Chapter 3. Conceptual select workflow. Imagine your application needs to display a specific user's profile. It would first obtain a database connection from the pool. Then, it would prepare a select statement like select username, email from users where id equals, with a placeholder for the user ID. The actual user ID, perhaps obtained from a web request, would be passed as a parameter to the execute function. After execution, the application would call a fetch-one method to get the single user record. This record could then be used to populate a web page or an object in your application's memory. Insert, update, delete, and checking affected rows. For data modification queries, DML, the process is similar. Prepare and execute, construct the SQL insert into, update, delete from, with placeholders and pass parameters. Check results. The database typically returns information about the operation, such as affected rows, the number of rows that were inserted, updated, or deleted. This is crucial for user feedback and application logic. Last insert ID. For insert statements into tables with AUTOINCRMENT primary keys, the ID of the newly inserted row is often returned. Conceptual insert workflow. Let's say a new user signs up. Your application would get a connection. It would then prepare an insert statement for the user's table, including placeholders for the username, email, and password hash. The user's input values would be provided as parameters. After executing this statement, your application would typically retrieve the last inserted ID to get the primary key of the new user, which it might then use for further operations like logging the user in or creating a default profile. Using parameterized queries, prepared statements in practice. As highlighted in Chapter 9, parameterized queries are your primary defense against SQL injection. Every database driver and ORM you use will have a way to implement them. The syntax varies, but the principle is consistent. Separate the SQL query logic from the data values. Conceptual parameterized query. Instead of manually building an SQL string where you insert user-provided variables directly into the query, which is highly vulnerable to attack, you send the SQL template with placeholders to the database. For example, you might write, select from products where category equals, and price. Then, you provide the category name and the maximum price as separate parameters. The database now knows exactly which parts are commands and which parts are just data, preventing malicious input from being executed as SQL. Handling transactions in application code. The start transaction, commit, and rollback commands from Chapter 7 are controlled by your application logic. This is essential for maintaining data integrity when multiple database operations must succeed or fail as a single unit. A typical pattern involves start a transaction, connection begin transaction, or equivalent. Execute multiple SQL statements. Perform your inserts, updates, deletes. Handle success failure. If all operations complete without error, commit the transaction, connection.commit. If any operation fails or an exception occurs, roll back the transaction, connection rollback. Ensure cleanup. Always make sure the transaction is either committed or rolled back, usually in a try, except, finally block or try catch finally in some languages. If you don't commit or roll back explicitly, the database might eventually roll back the transaction automatically, but this is usually undesired behavior. Conceptual transaction workflow. Imagine a process to move funds from one account to another within your application. First, you'd signal the start of a transaction to your database connection. Then, you'd execute a SQL update to reduce the balance of the source account. Immediately after, you'd execute another SQL update to increase the balance of the destination account. If both of these update operations succeed and your application logic indicates no further problems, you then tell the connection to commit the transaction, making both changes permanent. Crucially, if for any reason, like insufficient funds or a database error, the first update fails or the second update fails, your application would catch that error and then command a rollback, ensuring that none of the changes are saved to the database and the balances remain consistent. 10.3 Introduction to Object Relational Mappers, ORMs. Working with raw SQL can be powerful, but it also means writing a lot of repetitive code to map database rows to programming language objects. This is where Object Relational Mappers, ORMs, come in. An ORM is a programming technique that converts data between incompatible type systems using object-oriented programming languages. In simpler terms, it's a layer of abstraction that allows you to interact with your database using objects and methods from your programming language, rather than writing raw SQL. Example conceptual using ORM instead of raw SQL. Raw SQL. Select username, email from users where id equals 1. ORM equivalent conceptual. User find bid 1 or session query user. Filter b ID equals 1. First. Raw SQL. Insert into users, username, email values, newser, new at example.com. ORM equivalent conceptual. Newser equals user, username equals newser, email equals new at example.com, session add newser, session.commit. Popular ORMs, Python, SQL Alchemy, Django ORM, Peewee. Node.js, Sequelize, TypeORM, Prisma. PHP, Eloquent Laravel, Doctrine. Ruby, Active Record Rails. Java, Hibernate JPA. Pros of using an ORM, productivity, faster development due to less boilerplate SQL. Abstraction, you work with familiar programming language objects instead of SQL tables and columns. This abstracts away database-specific SQL syntax differences. Built-in security. ORMs generally use parameterized queries by default, helping prevent SQL injection. Type safety. In statically typed languages, ORMs bring type safety to your database interactions. Database agnostic to an extent. Some ORMs allow you to switch database backends, e.g., from MySQL to PostgreSQL, with minimal code changes. though this benefit is often overstated in practice for complex applications. Cons of using an ORM: performance overhead. The abstraction layer can introduce some performance overhead compared to finely tuned raw SQL, especially for complex queries. Impedance mismatch. The relational model, tables, rows, and the object-oriented model, objects, inheritance are fundamentally different. Mapping between them can lead to complexities. Learning curve. ORMs have their own specific APIs and conventions to learn. Leaky abstraction. For complex or highly optimized queries, you often need to drop down to raw SQL or understand the SQL the ORM generates, defeating some of the benefits of abstraction. Forcing an ORM to do very complex joins or aggregations can sometimes result in inefficient SQL queries. When to use raw SQL versus ORM. Use ORM for standard CRUD operations. Most reads and writes that map directly to single objects. Rapid development, when quick iteration and boilerplate reduction are priorities. Many-to-one, one-to-many relationships. Simple traversals. Built-in features. Leveraging ORM's caching, validation, or migration tools. Use raw SQL for complex, optimized queries, where performance is critical and an ORM might generate inefficient SQL, e.g., complex reports, bulk operations. Database-specific features. Utilizing advanced MySQL features not well supported by your ORM. Legacy databases. Interacting with existing, potentially poorly designed schemas. Database migrations. Changing schema or bulk data loading. Many applications use a hybrid approach. ORM for most common operations and raw SQL for specific performance-critical or highly complex queries. 10.4 Example snippets. Conceptual. To make the integration tangible, let's walk through conceptual examples for a blog post service. Remember, these are descriptions of logical steps, not specific code syntax for a particular language, to be audio-friendly. 1. Connecting to MySQL conceptual. Your application would first load its configuration, which includes the database host, username, and password. It would then use the database client library for your programming language to create a connection pool. This pool would be initialized with a certain number of open connections ready for use. When a web request comes in, a connection is efficiently retrieved from this pool, rather than creating a brand new one. 2. Executing a simple select query for a post, conceptual. Upon receiving a request to view a blog post with a specific ID, the application obtains a connection from its pool. It then composes a select statement. Select title, content, publish edit from posts where id equals. The post ID from the request is passed as a parameter separately from this SQL string. The database driver then executes this parameterized query. The single resulting row, containing the title, content, and publication date, is fetched into the application, which then renders it for display on a web page. 3. Executing an insert with parameters for a new comment, conceptual. When a user submits a new comment, the application receives the comment text, the post ID, and the user's ID. Using a database connection, it prepares an insert statement for the comments table, with placeholders for these values. Insert into comments, posted, userid, content values. The actual values are bound to these parameters, and the statement is executed. The application might then check if exactly one row was affected, indicating a successful comment creation. 4. Implementing a basic transaction, conceptual. Consider a scenario where you need to archive a post, which involves updating its status in the posts table and simultaneously inserting a record into an archive-slog table. Your application would first tell the database connection to begin a transaction. It would then execute an update query to change the post's status. Following this, it would execute an insert query to add an entry to the archive-slog. If both operations succeed without error, the application calls commit on the transaction. However, if anything goes wrong during either the update or the insert, an error is caught, and the application calls rollback on the transaction. This ensures that either both or neither of the database changes are permanently saved, maintaining data consistency. 10.5 Best practices for application interaction. To write high-quality, performant, and reliable applications that interact with MySQL. Consider these best practices. Resource management, closing connections. Always ensure database connections are properly closed or returned to the pool once they are no longer needed. Many languages and frameworks provide try with resources, Java, or with statements, Python, that handle this automatically, preventing resource leaks. Leaving connections open unnecessarily can exhaust your max connections limit on the MySQL server, leading to application downtime. Error handling and logging. Implement robust error handling around all database operations. Catch exceptions thrown by your database driver ORM. Log detailed error messages, including the SQL query, without sensitive data, parameters used, and the full exception traceback. This is invaluable for debugging production issues. Distinguish between transient errors, e.g., network timeout, deadlock, that can be retried, and persistent errors, e.g., invalid SQL constraint violation, that require application logic changes or user notification. The N+1 query problem and how to avoid it. What it is. A common performance anti-pattern where an application makes one query to fetch some initial data, n rows, and then, for each of those n rows, makes an additional query to fetch related data. This results in N+1 queries instead of a single, more efficient query. Example in our blog, fetching 10 posts, and then for each post asterisk, executing a separate query to get the author's username. This would be one query for posts plus 10 queries for authors equals 11 queries. Solution. Use joins, covered in Chapter 4, in your initial select query to fetch all necessary related data in a single round trip to the database. Many ORMs offer eager loading or preloading mechanisms that achieve this by default. Batching operations. If you need to perform many inserts or updates, especially in a one-off script or data import, it's often much more efficient to batch them into a single query. Instead of 1,000 individual insert statements, you can often write a single insert statement with multiple value sets. Insert into table, call 1, call 2 values, v1a, v1b, v2a, v2b, v1000a, v1000b. This significantly reduces network round trips and execution overhead. Similarly, update and delete operations can often be batched using where-in clauses for specific IDs. Summary of Chapter 10. You've successfully connected your application to MySQL and explored the essential techniques for interacting with your data. You now understand how to establish and manage connections to MySQL, appreciating the importance of connection pooling for performance and scalability. The fundamental patterns for executing select, insert, update, and delete queries from your application code, including retrieving results and checking affected rows. The critical role of parameterized queries, prepared statements, as your primary defense against SQL injection. How to manage transactions, begin, commit, rollback programmatically within your application code to ensure data integrity. The purpose, benefits, and trade-offs of object relational mappers, ORMs, and when to choose an ORM versus raw SQL. Key best practices for application database interaction, including proper resource management, error handling, avoiding the N+1 query problem, and batching operations for efficiency. This chapter forms the practical bridge between your database knowledge and your application development. With these skills, you'll be able to build robust, secure, and performant applications that leverage the full power of MySQL. Next, we'll shift focus to MySQL operations. Backup, restore, and monitoring, crucial aspects for maintaining your database in any environment beyond basic development. Chapter 11, MySQL Operations. Backup, restore, and monitoring. As a developer, your primary focus is often on building features and writing code. However, working with databases demands an understanding of their operational aspects. What happens if your server crashes? How do you move data between environments? How do you know if your database is performing well in production? This chapter delves into essential MySQL operations, backup and restore for disaster recovery, and monitoring for maintaining health and performance. While full-scale database administration is a specialized role, understanding these fundamentals is crucial for any developer whose application relies heavily on a database. Knowing how to protect your data and observe your database's behavior fundamentally influences how you design and deploy your applications. 11.1 The importance of backups. Data is often the most valuable asset of any application. Without a robust backup strategy, a single failure event, whether hardware malfunction, data corruption, accidental deletion, or malicious attack, can lead to irreversible data loss and catastrophic consequences for your application and business. Why backups are essential. Disaster recovery, recovering from hardware failure, disk crash, server outage, data corruption, restoring data after software bugs or human error corrupts the database. Human error, undoing accidental delete or update statements without a where clause. Security incidents, recovering from data manipulation or deletion by an attacker. Compliance. Many regulatory requirements, e.g., GDPR, HIPAA, mandate data retention and recovery capabilities. Recovery point objective RPO and recovery time objective RTO. These two metrics are crucial for defining your backup strategy. Recovery point objective RPO. This defines the maximum acceptable amount of data, measured in time, that you can afford to lose from your critical database. If your RPO is 1 hour, it means you can afford to lose at most 1 hour's worth of data changes. A shorter RPO requires more frequent backups or continuous replication. Recovery time objective, RTO. This defines the maximum acceptable downtime you can endure. It's the target time within which a business process must be restored after a disaster to avoid unacceptable consequences. A shorter RTO requires faster recovery mechanisms and often more redundant infrastructure. Your application's criticality directly dictates your RPO and RTO, which in turn dictate your backup and replication strategy. 11.2 Logical backups with MySQL. MySQL is a command line utility provided by MySQL that performs logical backups. It creates SQL statements, create table, insert, etc., that can be re-executed to reconstruct the database. This makes it highly flexible for restoring on different MySQL versions or even different database systems. Backing up a single database. MySQL U username, p database name backup SQL. Explanation for audio. This command logs in as username, password will be prompted, connects to database name, and outputs all its schema and data as SQL statements into a file named backup SQL. Example, backing up our blogclitform database. MySQL u root p blogclitform backup $date plus % y % m % d % h % m % s SQL. This saves the backup to a file with a timestamp in its name, like blogclitform backup 20,230,1,027,153,000. SQL. Backing up multiple databases. MySQL u username p databases db1 db2 db3 multipleds backup SQL. Backing up all databases. MySQL u username p all databases alds backup SQL. Important MySQL options. No data, dumps only the table schema, no data. Useful for schema migrations or creating empty development databases. MySQL u root p no data blogclitform schema SQL. Routines. Includes stored procedures and functions in the dump. Triggers. Includes triggers in the dump. Single transaction. Crucial for in no DB tables. This option performs the dump within a single transaction, ensuring a consistent snapshot of the data even if your application is writing to the database during the backup. Without this, especially for large, busy tables, your backup might be inconsistent. MySQL u root p, single transaction, blogclitform consistent backup SQL. Compress, compresses the output, saving disk space. Add drop database, adds a drop database if exisds statement before create database in the dump file. Useful for clean restores. Set gtid purged equals OFF, important for replication setups. Restoring from a MySQL file. Restoring is typically done using the MySQL client utility. Create the database. If it doesn't exist, create database blogclitform, restore the data. MySQL u username p database name backup SQL. Explanation for audio. This command pipes the SQL statements from backup SQL directly into the MySQL client, which then executes them against database name. Example, restoring bloglet form from a backup file. MySQL root p bloglet form backup, SQL. Limitations of MySQL dump for very large databases. While versatile, MySQL dump can be slow and resource-intensive for extremely large databases, hundreds of GBs to TBS, because it dumps data row by row as SQL statements. Restoring such dumps can also take a very long time. 11.3 Introduction to MySQL Pump, MySQL 8.0 Plus. MySQL Pump is a newer client utility introduced in MySQL 5.7 and improved in MySQL 8.0. It's designed to be a faster and more efficient alternative to MySQL dump for logical backups, especially for large databases. Benefits over MySQL dump: parallel processing. MySQL Pump can dump databases and tables in parallel, significantly speeding up the backup process. Compressed output supports compressed output by default, though MySQL dump can also do this. Include filters. More flexible options for including or excluding specific databases, tables, or regular expressions. User information can include user accounts and grants in the dump directly. Basic usage. MySQL Pump username. P default parallelism equals 4 databases bloglet form pump backup SQL. Explanation for audio. This command backs up the bloglet form database using MySQL Pump, leveraging 4 parallel threads. Default parallelism equals 4 to speed up the process. For advanced usage, refer to MySQL documentation. For restoration, you generally use the MySQL client, just like with MySQL dump output. 11.4 Incidental mention of physical backups. For very large, mission-critical production databases, physical backups are often preferred for their speed and efficiency, especially during restoration. How they work. Physical backups directly copy the actual data files and log files from the server's data directory. They are much faster because no parsing or SQL statement generation is involved. Restoration is also faster as it's a direct file copy. Types: hot backups, performed while the database is running and actively processing transactions, minimizing downtime. Cold backups, performed while the database is shut down. Simpler but requires downtime. Commercial tools. MySQL Enterprise Backup is a commercial solution specifically designed for hot physical backups of InnoDB. Open source alternatives. Percona Extra Backup, open source, is a highly popular and robust tool for non-blocking physical backups of InnoDB. Binary logs, binlog, for point-in-time recovery, conceptual. The binary log, binlog, is a record of all data-modifying statements and changes that have occurred in your MySQL server. It's primarily used for replication, sending changes to replica servers. Point-in-time recovery, PITR, the ability to restore your database to a specific moment in time, e.g., just before an accidental delete occurred. This is achieved by first restoring a full backup, e.g., from MySQL dump taken at 2 a.m. Then, you apply the binary log events from the backup time up to your desired point in time, omitting the problematic query. This provides a very low RPO, but it requires continuous binary logging and careful management. 11.5 Basic monitoring for developers. Monitoring helps you understand the health, performance, and workload of your MySQL database. As a developer, basic monitoring helps you detect issues caused by your application's queries and prevent small problems from escalating. Show PROCSSLISD for active queries. As mentioned in Chapter 6, show PROCSSLISD, or show full PROCSSLISD, is your go-to command for seeing what queries MySQL is currently executing. Show full PROCSSLISD. Explanation for audio. This command lists all active connections to the MySQL server, showing the user, host, database, command, query, sleep, etc., amount of time the command has been running time, its current state, and the full SQL query text. Look for long-running queries, time column from your application, especially those stuck in a particular state. Understanding MySQL status variables, show status. MySQL maintains hundreds of status variables that provide insights into server activity, resource usage, and performance. Show global status like in nodbufferpool%, show global status like comSelect, count of select statements, show global status like handleRead%, Indicators of red patterns, e.g., R&D Next suggests full table scans. Explanation for audio. These commands allow you to inspect specific status variables. For example, in nodbuffer pull read requests and in nodbuffer pull reads can indicate how efficiently the buffer pool is operating. A lower ratio of reads to read requests is better, indicating more data is served from memory cache. A high handle read in Next might suggest a lot of full table scans. Basic operating system tools for monitoring. Don't forget the tools available on your server's operating system. CPU. Top HTOP Linux Mac OS, Task Manager Windows. Is MySQL consuming all CPU? Memory. Free H Linux, Activity Monitor Mac OS. Is MySQL hitting memory limits? Is swap being used? Disk I/O, IOStat X1 Linux, IOTOP Linux. Is the disk a bottleneck? Are reads writes high? Network, Netstat Punta Linux. These help determine if the database bottleneck is due to resource exhaustion at the OS level. Overview of professional monitoring tools. For production environments, relying solely on command line tools is impractical. Dedicated monitoring solutions provide real-time dashboards, historical data, alerting, and integration with your IT infrastructure. Prometheus and Grafana, an industry standard for open-source monitoring. Prometheus scrapes metrics from MySQL exporters and Grafana visualizes them, highly customizable. Percona Monitoring and Management, PMM, a free and open-source platform specifically for MySQL, PostgreSQL, and MongoDB. It offers in-depth dashboards for query analysis, server health, and more, providing insights beyond what simple metrics can offer. Cloud Provider Managed Services. If you're using a managed database service like Oz RDS, Google Cloud SQL, or Azure Database for MySQL, they provide extensive built-in monitoring, metrics, and logs accessible through their dashboards and APIs. They handle much of the underlying infrastructure monitoring for you. 11.6 Routine Maintenance Tasks. While InnoDB databases generally require less manual maintenance than older database systems, a few routine tasks are still relevant. Optimizing tables, rarely needed for InnoDB. Older storage engines, like MyISAM, could suffer from fragmentation, requiring optimized table to defragment and reclaim space. For InnoDB, optimized table performs a table rebuild, which can be a lengthy blocking operation for large tables. InnoDB often manages its space efficiently, and external fragmentation is usually handled at the operating system level. Only run optimized table if you have specific evidence it's needed, e.g., a very large table with a lot of deleted rows not reclaiming space, or if indexes are severely fragmented despite other methods. Checking and repairing tables. Check table, repair table. These commands are used to check for and fix corruption in tables. For InnoDB, check table primarily checks the table structure and its index. InnoDB is generally self-healing due to its transactional logs and crash recovery mechanisms. Repair table is useful for MyISAM tables to fix corruption after a crash, but it doesn't do much for InnoDB as its recovery is automatic. Regular backups are your primary defense against corruption rather than relying on repair operations. Summary of Chapter 11. Understanding MySQL operations is crucial for building and maintaining reliable applications. You've gained insight into the paramount importance of backups, guided by RPO and RTO targets. Performing logical backups using MySQLdump, the workhorse, and MySQLpump, the modern, faster alternative, including crucial options like single transaction. The basics of restoring a database from a logical backup. A conceptual understanding of physical backups and the role of binary logs for point-in-time recovery. Essential monitoring techniques for developers. Using show PROCSSLIST for active queries, show status for server metrics, and leveraging OS tools for resource checks. An overview of professional monitoring solutions, Prometheus/Grafana, PMM, and cloud-managed services. Briefly touched upon routine maintenance tasks and why they are less frequent for InnoDB. Armed with this knowledge, you are better prepared to interact with, manage, and troubleshoot the MySQL databases that power your applications. This operational awareness makes you a more complete and valuable developer. In our final chapter, we'll explore advanced topics and best practices for developers, bringing together many concepts and looking at what's next. Chapter 12. Advanced Topics and Best Practices for Developers. Congratulations! You've journeyed from MySQL fundamentals to advanced querying, performance tuning, transaction management, database security, and essential operations. You now possess a comprehensive understanding of MySQL from a developer's perspective. In this final chapter, we'll delve into a few advanced topics that are good to be aware of as your applications grow, revisit common pitfalls, and crystallize key best practices that will serve you well throughout your career. 12.1 Brief Introduction to Replication. As your application grows, a single MySQL server might struggle to handle the load, or you might need a plan for high availability. Replication is a core MySQL feature that allows you to maintain multiple copies of your database. Master-slave, source replica, architecture. The most common form of MySQL replication is asynchronous master-slave, officially. Source replica replication. Source master server. This is the primary database server where all write operations, insert, update, delete occur. Replica slave servers. These servers asynchronously receive a copy of the transactions committed on the source. They are primarily used for read operations or as hot standbys for disaster recovery. How it works. The role of binary logs. The foundation of MySQL replication is the binary log, binlog. Source writes to binlog. Each time a transaction is committed on the source server, MySQL writes a record of the changes, in terms of events or SQL statements, to its binary log. Replica reads binlog. The replica server has two threads, I/O thread, connects to the source, requests binary log events, and saves them to its own local relay log. SQL thread reads the events from the relay log and executes them on the replica's database, effectively mirroring the changes from the source. Benefits. Read scaling. By directing read queries to replica servers, you can distribute the read load, effectively scaling out your read capacity horizontally. This is common for busy web applications where reads significantly outnumber writes. High availability and disaster recovery. If the source server fails, you can promote one of the replicas to become the new source. This minimizes downtime. Data analytics. You can run long-running analytical queries on a replica without impacting the performance of your production source database. Backups. You can take backups from a replica server, reducing the load on your primary. Challenges. Asynchronous nature. Changes are applied to replicas with a slight delay, replication lag. If the source fails, recent transactions, those not yet replicated, might be lost. Failover complexity. Automatically detecting source failure and promoting a replica is not built into MySQL itself. This requires external tools or scripts, e.g., Orchestrator, MHA. Write scaling. Replication alone doesn't directly solve write scaling problems. All writes still go to the single source server. 12.2 Scaling Strategies, Conceptual. As your application matures, you'll inevitably hit scaling challenges. While database tuning and replication help, sometimes more drastic measures are needed. Vertical scaling versus horizontal scaling. Vertical scaling, scaling up. Upgrading to a more powerful server, more CPU, RAM, faster storage. Simpler but eventually hits limits and is more expensive. Horizontal scaling, scaling out, distributing the workload across multiple servers. More complex but offers near limitless potential. Replication is a form of horizontal scaling for reads. Read replicas for read scaling. As discussed, replicas decouple read traffic from write traffic. Your application logic needs to be smart enough to send select queries to replicas while sending insert, update, delete queries to the source. Sharding, horizontal partitioning. What it is. A technique to scale writes and reads for very large datasets by distributing data across multiple, independent database servers, shards. Each shard holds a distinct subset of the data, e.g., user IDs 1 to 1M on shard A, 1M 2M on shard B. When to consider. When a single database server, even with read replicas, can no longer handle the write volume or the total data volume. Challenges. Extremely complex to implement and manage. Requires careful design of a sharding key and often a routing layer in your application to direct queries to the correct shard. Cross-shard queries are difficult. Connection pooling revisited. This is an application-level scaling technique. As discussed in Chapter 10, connection pools provide efficient reuse of database connections, allowing your application to handle more user requests concurrently without overwhelming the database with new connection attempts. Caching strategies. Databases are disk-bound. Caching brings frequently accessed data into faster memory. Application-level caching, storing queried data directly within your application's memory or a dedicated cache server like Redis or Memcached. This avoids hitting the database altogether for certain reads. Database-level caching, MySQL's in no DB buffer pool, discussed in Chapter 6, is a powerful internal cache. Optimizing in NOD buffer pool size directly impacts how much data MySQL can cache in memory. When to use. Ideal for data that is read frequently, but changes infrequently, e.g., configuration settings, popular blog posts. 12.3 Common pitfalls and how to avoid them. You've learned many of these throughout the book, but they bear repeating as they are common sources of performance problems and bugs. Selecting all columns, select when not needed. Problem, retrieves unnecessary data, consuming network bandwidth and memory, and potentially preventing covering index usage. Solution, always explicitly list the columns you need. Lack of proper indexing. Problem, leads to slow select queries, especially for filtering, sorting, and joining large tables. Solution, use explain to identify slow queries and missing indexes. Index columns in WHERE, order by, group by, and join clauses. Prioritize higher cardinality columns. The n+1 query problem. Making an initial query fetch a list of items, then executing a separate query for each item to fetch its details. Results in many n+1 database round trips. Solution, use joins or ORM's eager loading to fetch all related data in a single query. Not handling transactions correctly. Problem, leads to data inconsistency, race conditions, or deadlocks if not properly managed. Commit, rollback, select. 4 Update. Solution, wrap all multi-step, dependent database operations in explicit transactions. Implement retry logic for deadlocks. Not using parameterized queries, SQL injection vulnerability. Problem, arguably the most dangerous and common security vulnerability. Directly inserting user input into SQL strings. Solution, always use parameterized queries, prepared statements for any user-provided input. Ignoring error messages. Problem, not logging or properly handling database errors can mask underlying issues like connectivity problems, constraint violations, or outright failures. Solution, implement robust error handling, log detailed error messages, and alert on critical failures. Distinguish between transient and persistent errors. Inadequate monitoring. Problem, lacking visibility into your database's health, performance, and workload. Makes it impossible to proactively identify and resolve issues before they impact users. Solution, set up basic monitoring for development and robust, real-time monitoring for production. Regularly review logs and metrics. Heavy reliance on select for count. Problem, while count ignores column contents, select from table where condition followed by count. On the result is often inefficient if an index can satisfy the count directly. Solution, use count judiciously. For counting rows matching a where condition, select count from table where condition is often optimized to use an index. For counting distinct values, count distinct column name is appropriate. Using text or blob columns for indexing filtering. Problem, text and blob types cannot be directly indexed as a whole. Solution, use prefix indexing, varchar, 255, or FULLTXT indexes where appropriate, or consider external search solutions. 12.4 Continuous integration / continuous deployment, CI/CD, with databases. Modern software development emphasizes continuous delivery. This extends to your database schema. Database migrations. Concept, a migration is a version-controlled script, e.g. SQL file that describes changes to your database schema and sometimes data. Tools, frameworks like Flyway and Liquibase, language independent, or ORM-centric tools like Django migrations, Alembic Python, and Doctrine migrations, PHP. Why? They provide a systematic, repeatable, and reversible way to evolve your database schema across different environments: development, staging, production. Schema versioning. Each migration script typically has a version number, and the tool tracks which versions have been applied to which database. Automating database changes. Integrate your migration tools into your CI/CD pipeline. When deploying a new version of your application, the pipeline should automatically apply any necessary database migrations. This ensures that your application code and database schema are always in sync. 12.5. The role of the DBA versus developer. As you delve deeper into database complexities, the line between developer and database administrator, DBA, can sometimes blur. Developer's role. Designing application-specific schemas, tables, columns, basic indexes. Writing efficient, secure, and correct SQL queries. Understanding transaction boundaries and concurrency within application logic. Implementing basic database integration, connection pooling, ORMs. Basic monitoring of application-generated queries. Suggesting and implementing index changes based on profiling. DBA's role. Overall database server health and lifecycle management. Advanced performance tuning, server configuration, complex queries, storage engine parameters. Robust backup and disaster recovery strategies, physical backups, point-in-time recovery, replication topologies. Security hardening at the server and network level. Capacity planning and scaling complex architectures, sharding, monitoring, alerting, and incident response. Collaboration is key. Effective teams involve close collaboration between developers and DBAs. Developers should write clear, debuggable SQL and understand DBA concerns. DBAs should provide guidance on schema design for scalability and performance and assist in deep query analysis. In smaller teams, developers might wear both hats, which makes this book's content even more critical. 12.6. What's next? Further learning. Your journey with MySQL doesn't end here. The database world is vast and constantly evolving. Here are some avenues for continued learning. Advanced MySQL administration. Dive deeper into replication, group replication, semi-synchronous, advanced backup strategies, Percona Extra backup, clustering e.g. MySQL NDB cluster, and detailed server configuration. Specific ORMs and frameworks. Master the ORM you choose for your primary development language, e.g. SQL Alchemy, Hibernate, Eloquent. Understand how it generates SQL and how to optimize its usage. Cloud database services. Explore managed MySQL services from cloud providers, AWS RDS, Google Cloud SQL, Azure Database for MySQL. These services handle much of the operational burden, backups, patches, scaling, allowing you to focus more on application development. NoSQL databases. While this book focused on relational databases, understand the strengths and weaknesses of NoSQL databases, e.g. MongoDB, Cassandra, Redis, and when they might be a better fit for certain types of data or use cases. Database design patterns. Explore advanced design patterns, data warehousing concepts, OLAP versus OLTP, and analytical databases. Advanced SQL features. Dive into more advanced SQL features like recursive CTEs, XML functions, or advanced JSON manipulation. Conclusion. You've embarked on and, hopefully, completed a comprehensive learning journey through MySQL for developers. You started with the basics of setting up your environment and designing a robust schema. You learned the fundamental operations of data manipulation and how to wield powerful SQL queries with joins, subqueries, and window functions. You then moved on to vital performance tuning techniques, leveraging indexes and explain to make your applications fast. Critical concepts of transaction management and database security were covered, ensuring your data remains consistent and protected. Finally, you explored how to integrate MySQL seamlessly with your application code and touched upon essential operational concerns like backup, restore, and monitoring. The knowledge and skills you've acquired are invaluable. Databases are the backbone of almost every modern application, and a deep understanding of how they work is a superpower for any developer. Keep experimenting, keep learning, and remember that with great database power comes great responsibility. Good luck and happy coding!